Hello, I hope I am audible. Yeah, so yes, I hope the screen is visible and I am audible. Yeah, so let's just start with the COA short notes. Uh, so let's just start. Let's just start it. So first, first there is a prerequisite that some other prerequisites are that if see in if in a question there will be given units given time and data, you have to check it because you have to take the values based on the unit. Like if the kilo is there, if the kilo is there, but if time is given, then you have to put kilo equal to 10 power 6. Okay. If data is there, okay. If data is there, then kilo equal to 2 power 10. Okay. Then same for mega. If mega is there, then 10 power 6. But if data is there, then it will be 2 power 20. Okay. Then giga. So for giga, Uh, so for giga, if if I check the time, if the unit is given in time, then giga is 10 power 9, and if the data is used, then it will be 2 power 30. Okay, so this is the some prerequisite. This is the prerequisite which I want to tell you. Yeah, everything works. Okay, so now moving to the next point. See, in a computer architecture, like in our architecture, if you look into the architecture, then there are three types of bus, right? Address bus which is unidirectional from CPU to memory. So there is a CPU here, there is a CPU here, and there is a memory here. Memory. So this is the address bus. It is the unidirectional. That is the address bus, or some IO. If some IO is happen, then also, right? So it is a unidirectional bus. Then then another is data bus. Data bus is bidirectional. So data bus is bidirectional. Bidirectional means that some data is been forwarded from CPU to memory and memory to CPU. So in both the direction. Okay. And control bus. What is the use of control bus? Control bus is used to send the control signals, right? Control signals. So that time to time CPU knows that what instruction to perform, and other stuff also, right? So is mainly used to transfer the control signals. Okay, okay. So there are three type of bus. So keep remember that there are three type of bus, which is address bus, data bus, and control bus. Okay. Now next point. See, if 32-bit architecture is given, means ALU is of 32 bits. MDR means data register, right? Message data register, and word size of CPU equal to 32 bits. So MDR means memory data register, memory data register, right? So you know it from the computer architecture course if you have done that whenever the instruction fetch happens, and then whenever you fetch the data from the memory, right? Whenever you fetch the data from the memory, so this MDR register, it is one type of register. It is called as MDR data register. So it is used to hold data. Here data will be stored. Okay. So if 32-bit architecture is given, so if in a question it is mentioned that if in a question it is mentioned that 32-bit architecture is used, 32-bit architecture, which means ALU. So ALU, you know, right? Arithmetic and logical unit. So it is of 32 bits, which means that it is able to perform the data of 32 bits. Okay. Then this MDI is of 32 bits. MDI is of 32 bits. And the word size. See, word size of CPU is also 32 bits. Okay. The word size of CPU is 32 bits. Now remember this point. Okay. Now moving to the next point. Moving to the next point. That by default memory is byte addressable. Right? By default memory is byte addressable. So there are two type of memory. There are two type of memory. Uh, byte addressable and word addressable. Byte addressable and word addressable. So by default memory is byte addressable, which means that what is byte addressable and word addressable? Which means that if you look into the memory, if you look into the memory, if it is a byte addressable, which means that one address contains one byte. Here, one byte will be there, one byte will be there, one byte will be there. Okay, each address contains one byte. If you see word addressable, if you see word addressable, then if you see word addressable, then one address contain one word. One address contain one word. Here, one word. Okay, so this is called as byte addressable and word addressable. So if nothing is given, then by default memory is byte addressable. Okay, memory is byte addressable. Okay, so now coming to the next point, word size of CPU and memory are two different things. Okay, word size of CPU. So there is the word size, the word of the word size of CPU and memory are two different things. Okay, so remember this point that CPU and memory both have different word size. Right? So memory you know this one and then CPU you know right? See here I have told that word size of CPU equal to 32 bits. Now see the next point to clear this. That if memory is given, okay, if memory is given word addressable, that your memory is word addressable. But this word size is not given. Okay, this word size is not given. This word size is not given. Then what size to consider for this word? So this word will be the word size of CPU. Okay, so this word will be word size of CPU if word size is not given. Okay, so if the word size is not given, then this word is equal to, so memory word is equal to word size of the CPU. And from the above point, you know that what is the word size of the CPU. If 32-bit architecture or some information, it will given, right? It will be given 100% given. So that is the word size of the CPU. Okay. So keep remember this point as well. Keep remember this point as well. If the memory is given word addressable but size is not given, then then consider one word size equal to word size of the CPU. Okay. Now moving to the next point. Moving to the next point. So micro operation. Right? What is the micro operation? The smallest operation which CPU can execute in a single step. So what is the micro operation? Which means that smallest operation. So smallest operation which CPU can execute it. A CPU can execute smallest operation in a single step. So what the single step? So what in a single step a CPU can execute? That smallest operation is called as micro operation. Okay, and time taken to execute it. So time taken to execute that one micro operation. Okay, so time taken to execute that one micro operation is called CPU cycle time. Keep remember this. Keep remember this. What is the CPU cycle time here? Because in a computer architecture, this word comes too frequent, like cycle time. What is the cycle time and all that? So what is it? So time taken to execute one micro operation. Okay, time taken to execute one micro operation. And what is micro operation? Smallest operation CPU can execute in a single step. Okay, so in a single step, what is the smallest operation a CPU can execute? So these are the some prerequisites which I need to cover it. Okay, before moving to some particular topic. Okay, so let's just now move to the next topic. Okay, so cache organization, right? So cache organization. The next topic is the cache organization. Everything related to cache. Everything related to cache, which in the gate exam it is very helpful. Let's go. I have made the short notes in keeping all everything I have covered, like everything I have covered which is coming in the gate. So in this short note, you will find that each and every point which is useful in the gate, and also it will most probably come in the gate, and it have come in the gate. So if you see these short notes, then you will get the complete revision of computer architecture course. Okay. So let first point. So first point is there are two localities, right? There are two localities, which is spatial and temporal locality. So you know, right, that there are two type of locality, spatial and temporal. So what is the spatial means? Everything to space. Spatial means space, and temporal means time. So spatial means that if you have access this address, if you have access x1 and it is called as x2, right? So if you have access the address x1, if you have access the address x1, then most probability you will access the address x2. You will most probable for the next request you will access x2. Okay, so that is called as spatial, which means that if a particular block will come, you will be so this has to do with the block. Like in a block, many addresses are present, right? Many addresses are present. The block contains many addresses. So if you access this one, so in a most probable that for the next request you will access its immediate address. So it is called as spatial. And temporal means that if you access the address x1, if you access the address x1, if you have access the address x1, then most probable that for the next request also you will request x1. So next time x1, again x1, again x1. So same x1, x1, x1. If you request it, it is called as temporal locality. Okay, it's called as temporal locality. So it's a very easy concept, spatial and temporal. Okay, so now moving to the next point, that there are three type of mapping. There are three type of mapping: direct, set associative, and fully associative. Okay, so keep remember it that there are three type of mapping: direct, set associative, and fully associative. So in above uh, in like below, I have covered it, so no need to worry. Okay, so next point is cache memory is not addressable, it's indexable. Okay, cache memory is not addressable. Cache memory don't have address, but cache memory is not addressable, it's indexable. So which means that if this is the cache memory, you will here don't have address, it have index. It has index, right? It has index. This one is index. And you will access this particular block with the help of the index. You access with the help of the index. Okay, so these are the index. One more thing. Okay, so keep this point in mind. Okay, so one important point is coming, that block size of cache and main memory are same. Many times we tend to forget that what is the block size of cache is given at. So in every question, if you have done solve the gate PYQs, in every question block size of cache is given. Okay, but block size of main memory is not given. So you must have to assume that every time you have to assume that block size of cache and main memory are same. Right? Block size of cache and main memory are same. So block of cache memory is equals to block of main memory. Okay, every time you have to assume it. Now, next point, CPU always generates the main memory address by default, right? So you must know this thing that there is a CPU. There is a CPU, there is a main memory, and in between there is a cache. Okay, in between there is a cache. So CPU always generates the main memory address. Always generates the main memory address. So this point is telling that thing that CPU always generates the main memory address by default. Okay. Now this is the one another good point you need to take care. Line, block, and index all are same. Many times this thing people are forgetting that what is the line, what is the block, and what is the index. So each of these, which means that line, block, and index all are same. If anything is given in the question related to this, then you have to assume that line, block, and index all are same. Okay. Now next point, number of blocks in cache memory is equals to size of cache divided by block size. Okay. So if these are the formulas which I have covered directly. So if you have checked my IIC course in the EPT, in the rank improvement course, I have covered these things very well. That you don't have to mug up any of the formulas. Okay, so number of blocks in the cache memory is equal to, see, if size of cache is they will give. Okay, size of cache they will anyhow they will give. Block size they will give. So you just have to divide it, which means if you don't have to remember, you can do something like that. Let's say one block equal to 4 KB. For let's say 48 bytes. Okay, 48 bytes. And cache memory is given as 32 KB. Okay, so one block equal to 48 bytes. So if 32 KB is given, then how many blocks? So this is not a simple math. So which means that 32 KB divided by 48 bytes. Okay, so this is the calculation. This is the calculation which is which is mentioned here. That this one is size of cache divided by block size. Size of cache divided by block size. Okay, now moving to the next point, that if main memory address is given in decimal, then main memory block number is equal to flow of address in divided by block size. So keep remember this point. This is the one very good point. Many people don't know this point. Many people, and there is a PYQs also with this particular point. That if main memory address is given in decimal, so you will be given some address, main memory address in some decimal value like 1, 2, 3, 4, and 4, 3, something like that, right? Then how to find the block number? How to find the block number? You have to, this is the address, right? You have to divide it by block size, and you have to take the floor. You have to take the floor. That is a very, very important point. Very important point. Please take care. Please take care this point. Please take care this point. Okay. Main memory block number is equal to flow of address divided by block size. Okay. Address divided by block size. Okay. Now moving to the next point. Cache memory block number is equals to main memory block number modulo number of blocks in the cache memory. Okay, so in the above point, in this point, you will get main memory block number. Got it? This you will get main memory block number. Now you have to mod by total number of blocks. Total number of blocks you will get by this formula. Okay, by this formula you will get total number of blocks. Then if you mod it, which means that you will get the cache memory block number. So if this is your cache memory, so what is the block number, right? What is the block number or line or index? Got it? See here, right? Line, block, and index all are same. So once you get cache memory block number, if you mod it with total number of blocks. This is total number of blocks. If you mod it with the total number of blocks, then you will get that what is the cache block, right? What is the cache memory block number? What is the cache memory block number? This is also one very good point. Please take care of this. Now, moving to the next point, what is the set number? So, cache memory set number is equal to same main memory block number modulo number of sets in cache memory. So, if sets is given, right? So, if sets is given, so this is called if something like given that this is set one, this is set two, this is set three. So, you have to mod it with the total number of sets. If set number is asked. If block number is asked, then you have to mod it with total number of blocks. Okay, these are the very good point. Please take care. These are the very good point. Please take care. Okay. Now next point is number of sets in the cache memory. So what is the total number of sets in the cache memory? Number of blocks in cache memory divided by associativity, right? Associativity. So you must know this thing that what is the associativity. So okay, so I will be saying this associativity in further slide, but you please remember this that number of sets. If you want to find that how what is the total number of sets, so total number of blocks you can find it with this calculation, and also with this formula you can find total number of blocks. Then you have to divide it by associativity. If you divide it, then you will get that what is the total number of sets. Right? Why I was not saying here because in the further I have in the further slides, I have covered that say what is the set associated. In that only, I will explain what do I mean. Now, moving to the next point. Moving to the next point. What is the tag bits? What is the tag bits? Tag bits is maintained for each block in the cache, right? For each block in the cache. So, if this is your cache memory, okay. If this is the cache memory, if this is the cache memory, there are the blocks, right? They have blocks given. They have blocks given. Okay. So here the tag here this thing is tag, okay, this thing is tag, so this is called as tag, this is called as tag. A tag is for each and every block, right? Tag is maintained for each and every block in the cache, each and every block in the cache. And what is the use of tag? What is the use of tag? Right, so why what is the use? So it helps from this thing, right? From this thing, with the help of this thing, with the help of tag, we can get to know which block is present, okay, which block is present. So I have covered one very beautiful question in the IIC course related to tag, right? So what I've covered, which means that see if this is the block, if we are if we see many different blocks will be mapped here, right? Many different blocks will be mapped here. Okay, so now out of this particular thing, how we can get to know that which block is present and which block is present. Okay, which block is present, because many different address which can any many different blocks can be mapped in this particular line. Okay, in this particular block of cache. Okay, so how we can get to know with the help of the tag? We can get to know with the help of the tag by comparison. Okay, by comparison. This thing I think you must know if you have done any computer architecture course. Okay, and if you don't know what is the tag, I have explained it. So keep this thing in mind. There is one beautiful question I have covered also in with the and same concept, similar concept I have covered. Right. So now moving to the mapping. Okay, moving to the mappings. I am using the different colors to make it interesting. Okay. So there are three type of mapping which I have told here: diag mapping, set associative, and fully associative. Okay. So in that first one is diag associative. So what is diag associative? It is one-way set associative. It is one-way set associative. Okay, and what is one-way set associative means? One set is equals to one block, one way, right? One way, one here. What is one way? Which means that one block. Okay, one block. So each set contains one block. Each set contains one block, and you must know that what is the diag mapping or diag associative mapping. Okay, you must know. So each main memory block maps to exactly one cache line. Each main memory block maps to exactly one cache line. So if this is the case, and if this is the main memory block, right? This block maps to exactly one line, exactly only one line, right? Only one line, only any one line, any one line. So this is called as diag mapping. This is called as diag mapping. E- Each main memory block maps to only one cache line, right? Only one cache line. And how you can find it? How you can find it? If you know cache memory block number equal to main memory block number, like I have told you above formula, right? Mod total number of blocks, total blocks. With the help of this formula, see, this is the formula, right? With the help of this particular formula, with the help of this formula, you can able to find that where this main memory block will be mapped to this cache. Okay, and it is only maps to exactly one line, exactly one line. Keep remember this, exactly one cache line only. Okay, now if two blocks wants the same line, okay, so there might be happen that this is the block 1 b1 and this is the block b2. Okay, and this is the line they want, this is the line they wanted, this is the line they want. They both map to the same line, they both maps to the same line, which I told that it is called as conflict miss. And it is called as conflict miss because here both b1 and b2 is fighting, right? Both b1 and b2 is fighting for this particular block. Okay, so they both are conflicting with each other, and I have told you about this thing, like, right, that what is used here to identify which block is present. Let's say b1 block is present here. Okay, now how to identify that either b1 is there or b2 is there? With the help of tag, the help of tag. Okay, with the help of the tag you can able to identify that whether b1 is present or b2 is present. Okay, whether b1 is present or b2 is present. This is the very good concept. Please take care of this one, right? Now next point, what is the tag diacritic size? So tag diacritic size for all the mapping, right? All the mapping, which means that diag mapping, set associative, fully set associative, this formula is same. This formula is same, that total number of blocks in the cache into tag plus extra bits. So what is the tag diacritic size? Total blocks, total number of blocks, because I have told here tag is used for each block, right? Tag is used for each block. So total number of blocks into tag. What is the tag bit plus extra bits? Okay, if in a question extra bits are not given, then you can take zero. You can take zero if nothing is given. But extra bit is used for uh, different type of things like dirty bits, if you know, then modified bit, then excess bit. Some different types of bits are present, like they will be stored beside of tag, right? They will be stored beside of tag. These are called dirty. These are called different bits. Some extra bits are also stored for each blocks in the case, right? For each blocks in the case. So this is the tag diacritic size information. Okay, please take care this one. Now, my next point. No any replacement policy required for direct mapping as automatically replaced. Right. See, please take care this. Please take care this point. There is no replacement policy. There is no replacement policy, which means that if miss happens, then what to do? Something like that. Eh? Because replacement policy tells that if there is conflict, if there is a conflicting, right? If there is a miss, if like two party is right here if two party is uh, conflicting with each other, then which particular block do you replace? Like if got it. So when the replacement policy comes, if all blocks are full, right? Here also it is filled, here also filled, here filled, and here filled. If new block is come, then which to replace? At which block to replace? In this case, replacement policy used, right? Replacement policy is used. So no any replacement policy required for direct mapping is automatically replaced, right? So automatically replaced because here I have told that it maps to exactly one case line, right? With the help of this formula. With the help of this formula, it maps to only one case line. Like its address is fixed, address is fixed, right? Fixed location. Or you can say that address is fixed at fixed location. So that's why there is no any replacement policy. Okay. Now moving to the next point, that tag comparison equal to one comparator only, right? You have to only compare this one particular tag. Okay. If if you map to B1, right? If you map to this block, sorry for that, this let's say B4 block is come B4, and you map to this B4 is mapped to this particular block, right? B4 is mapped to this particular block. And you just have to compare it. You just compare this tag. Okay. Or if or if any request have occurred, right? Or if any request have occurred, you have to compare just one tag. So tag comparison, how? With the help of the comparator. So there is a comparator in the hardware and it is used to compare the things. Okay, so one comparator only. Now moving to the next point. What is the tag? So main memory address size minus log of cache memory size. Yeah, so same. This is in terms of bits. This is also in terms of bits. Okay, so yeah, so now some space I am creating here to explain the mapping formula. Okay, okay. Right. So this is the mapping formula. Like this is the formula for diag mapping. So this is the entire main memory address is given, right? This is the main memory address is given, and you can find its bits, right? This is the block size, right? This is the block size or block offset. Okay. Now this is the block size. So this entire is called as main memory block. Right? Main memory block. If you this is the if in a question it is only given that main memory address and block size, then you can find that which block, right? So with the help of these bits, main memory block, right? And and if this is also is given, okay. So this is the byte offset, right? So block size is given, you can easily find byte offset and cache memory block number, right? So cache memory block number, how you can find the cache memory block number? Cache memory block number is you can find with the help of log of total number of blocks, right? Total blocks in cache. Okay, this thing you can find with the help of log of block size, right? So these are in terms of bits. These are in terms of bits, so you can easily find this particular all information. Okay, and I explained about that how you can find total blocks in the cache memory. Okay, so with the help of that, you can find it. Also, this is the cache memory size, right? This is the cache memory size. So here this thing is log of cache size. If cache size is given, so these bits are the cache size. This is the cache size, right? This is the cache size. So please take care this thing. Please take care this diagram. Please take care this mapping formula. Like different parts contain what are the things. If in a question, if they ask, then you can easily answer, right? You can easily answer. So this is the mapping formula. This is the mapping formula. I hope you know this. I hope you know this because there is not much required. This you have to remember it that there is a tag, there is a tag, there is a cache memory block number and byte offset. Many times this block number is called as index or line number, index number or line number, right? I told above. Okay. Now moving to the next point, what are the advantages? So advantages it is simple and fast. It has cheap hardware, right? Because it is simple, right? You can easily find the address with the help of this information. Then only one comparator is required. So hardware is also cheap and everything is simple and fast. The simple formula is being used here, and this is the simple mapping. And this is the simple mapping. Also, it is easy to implement. Okay. Also, it is easy to implement. Right. Now, what is the disadvantage? What is the disadvantage? Disadvantage is high conflict miss. Right. High conflict miss. High conflict miss, which means that here high conflict means that which means that too many many different blocks is fighting for this particular block, right? Is fighting for this particular block. So because their address are fixed, right? I told here that their address are fixed. See here, they are fixed location, which means that they can't go even if space is there, right? Even if space is present in the cache, right? Even if space is there, they can't go to the different location because they have fixed location. So they have because of fixed location, many misses will be there, right? Misses will be there, and each different block is fighting for their position. Blocks are fighting for its place, right? So high conflict misses occurred in this particular mapping. Okay. Now moving to the next mapping, which is called as set associative. So what is there in the set associative? So cache is divided into sets. Each set has k lines. So if someone tells that k way set associative, which means that each set have k lines or k blocks. Okay. So if this is the cache, if this is your cache, right? This is your cache memory. This is your cache memory. Cache is divided into sets. So it is divided into sets, and each set has k blocks. So let's say k equal to 2. So this is one set, it contains two blocks. Then this is another set, it contains two blocks. Contains another set, it contains two blocks. Okay. Okay. So now we have divided our sets. We have divided our blocks into sets, right? So cache memory is divided into sets. Now cache memory is divided into set. Now what is index in set associative, right? What is index? This one is set number, right? Set number. How you can find if block number is given, right? If block number is given, right? How you can do index in the set associated with the help of the set number, right? With the help of set number. Okay. Now next point. Moving to the next point. So a block can go to any line within one set, right? A block can go to any line within one set. So I have explained now this thing. See, number of sets. See, okay, I will explain this point. The number of sets equal to number of blocks divided by associativity. Okay. So what do I mean here? That let's say one block, uh, that you have to find the total number of sets, now, right? You have to find the total sets. So here, based on the associativity, you can get to know that one set contains, what is the k way means? One set contains k blocks, right? Here, each set contains k line. So if k equal to 2, which means that one set contains k way, okay. So k way or k blocks. So if you have total blocks, how you can find sets? So total blocks divided by k way, you can get total sets, right? So that is the same formula which I have written here. Number of sets equal to number of blocks in cache memory divided by associativity, right? Divided by associativity. This, please keep this thing in mind. Okay. Now a block can go to any line within one set. So if you have this block number, right? If you have this main memory block number, how you can find that which set to go? How you can find that which set to go with the help of this formula? See, I have told here only explained it. I have explained somewhere. Yeah, yeah, here. Cache memory set number. Cache memory set number is equal to main memory block number modulo number of sets, right? Number of sets. Got it? So number of sets, total number of sets you can find with the help of this formula. And then once you know main memory block number, if you do mod with total set, you can get to know what is the set number, right? What is the set number, which means that where this particular block, in which set this particular block will go, right? With the help of this formula, right? Very easy concept. Okay, very easy concept. And in this set also, it can go to any line, which means that a block can go to any line within one set. So if this is the S1 set, let's say if block has gone to S1 set, in S1 set also it can go to either here or either here, right? Anyway, because it can go to any particular block of the set. It represents the set, not the particular block in the set. Okay, right? Now, here this is one point I will cover sometime after these 2 points. Okay, now let's see this one. What is the total number of comparator? Which means that what is the total number of comparator? How many comparators required for the tag, right? For the tag. So k. So k comparators are required, which means that if the set is k associative, if the set is k associative, so this is one set, right? It is k way associative. So a set contains k blocks, right? This is said it contains k block. Okay, and here one tag is there, one tag is there, one tag and one tag is there, right? Now here, if we have to find out that, right? If we have to find that which block is present, you have to find each block in the set, right? So this. You have to find this all things parallelly. All the bits you can. This is the tag, right? This is the tag. So k comparators, right? K comparators with the help of this requested block, right? This is the requested. If this is the requested block, you can compare with the help of these all blocks present in the set, right? Because if this is the block, then you have to find that where this block is present. And I have told here, right? A block can go to any line, right? Any line within one set. In one set, a block can go to any line. So if a set is k way, you have to compare with the k blocks, right? With the k blocks, you have to compare. So that's why here it is told that number of comparators equal to k. and this is called as COA set associative cache. Okay. Now this is the main memory address mapping in the set associative mapping, right? This is the mapping for it. Like this is the main memory address, right? This is the main memory address. Okay. This is the block number. I have told this thing, right? This is the tag which you know. What is the set offset? Set offset is equal to log of total number of sets, right? Total number of sets. And there is one important formula which you have to remember this thing, that you can, if someone have given you cache memory size and associativity is given, yeah, you can do it by solving by calculating total number of blocks, right? uh, and all. But easily, if you want to find it easily, then this thing is equals to log of cache memory size minus log of associativity, right? Log of associativity. Okay, this first thing, right? Yeah. So if in a question, let's say a block size is not given, right? This is given. Block size is not given. Block size is not given. You want to find that what is the tag. You want to find what is the tag. So you can easily find with the help of this thing. See here, total main memory address, minus log of cache memory size minus this particular log of associativity, right? And then you can easily able to find the tag. So this is one particular very important point, right? This is one thing they can ask in the gate examination. They can ask in the gate examination, right? So please take care this formula. Please take care this formula, that what this part also represented, what this part represents. Yeah, this is the minus sign. This is the minus sign. Okay. Now, with the help of this same thing, this point is like if associativity is doubled, set number reduces by one and the tag increases by one. Right? So what does it mean? Let's say associativity is doubled, right? So associativity is two, now it doubled and it came to four, right? It came to four. Okay. So now if associativity is double, set total sets will be reduced, right? Total sets will be reduced. Okay, total set is reduced because here one set equal to two blocks. Here now one set equal to four blocks, right? So total sets will be reduced, right? So if total sets will reduce, which means that this bit will reduce, right? This bit will reduce. Now this bit will go this side, right? These bits will reduce. Set offset bit will reduce. Set offset bits reduces, okay, reduces, right? And then there will be more tag, right? Then there will be more tag, which means that tag bits increases. Okay. So this is the relation for this thing, that for means how much quantity it can increase and decrease, right? So if associativity is double, set number reduces by one and tag increases by one. Okay, very important point. Please take care this one as well. Okay. Now replacement policy, right? Replacement policy are uh, okay, what I required within a set, right? See, okay, this is not replacement policy. These are the three replacement policy. Okay, yeah. Maybe I am into that here, yeah, yeah. These are the replacement policy. These are the replacement policy. What I mean here, that in a set, this is the required, right? Replacement policy is required. So let's say this is the set and this is the one set and four blocks, right? Four blocks. One set contains four blocks, which means four way, Right. Now this is also full, this is full, this is full, and this is full. Now if one block maps to this set, block maps to this set, which to replace, right? Which block to replace, right? Which block to replace based on this replacement policy, based on the replacement policy. So this one is least recently used. I hope you know this least recently used. Then first in, first out, then random. This is the random, right? So these type of different policies are replacement policies are used here. There is most common. Like, there are too many questions related to this thing. Least, it is also called as least recently used. What does it mean? Replace the block, which means that replace the, what does it mean? Replace the block which is used least recent, right? So you have to replace that particular block which you have to replace that particular block which is used very least, right? Very least, right? Very least. If a particular block is used, you have to replace it. Okay. If you know it, first in, first out, first in, first out. So whichever comes first, you have to replace that. Right? And random is you can randomly replace any block, right? Randomly replace any block. So this is the replacement policy. Now there is some advantages. Yeah. So here fewer conflict means than direct mapping, right? Fewer conflict means and faster than fully associative. It is faster than fully associative, but it has fewer conflict means, right? Fewer conflict means. So I hope you got it. Why the fully? Why it has few conflict means, right? Because you know na, right? A set contains many block, right? So any block, if this is full, a block can be filled here, right? A block can fill here or here or here, right? So there is no conflict for it. But if I have told here, right? I have told here that in a direct mapping here, if many requests comes, right? Many requests come, this block is fixed, right? So here many conflict misses in the direct, but fewer conflict misses in the set associative, right? In the set associative. What is the disadvantage? It has slightly more hardware, right? Because k comparators are used. K comparators. You have to compare many things, right? You have to compare it many things. Okay. Now moving to the next point, which is called as fully associative, right? Fully associative. So what it is the most flexible mapping, right? It is the most flexible mapping. A main memory block can go to any cache line, right? Here there is no restriction. So what is the fully associative? Other name is that one set is equals to total blocks in cache. Okay, so it is if total blocks are x, right? So it is x-way associative, x-way associative, and only there is one set, right? Only one set here. Okay, which means that if this is the cache memory, only one set, right? Only one set in the fully associative. So a main memory block can go to any cache line, right? A main memory can block can a block can go to any cache line, either here, or here. There is no fixed position. Okay, there is no fixed position. Comparators required equal to number of cache lines, right? Because you have to compare each thing. You have to compare each particular lines, right? Each particular line to get to know. So comparator required a number of cache lines. Okay. Now in a fully associative mapping, tag is equal to main memory block number. Okay. So let's say if this is the mapping formula. This is the mapping formula that any block can go to any line because only one set, right? So if this is the main memory address, right? I told you, right, that this is the block size, how you can find it, and this is the main memory block number, and this is the main memory block number I told you, right? In the diag mapping, see here in the diag mapping I told you this is the main memory block number, right? Yeah, you divide the block size, and whatever bits you remain, those are the main memory block number. So here in fully associative, tag is equals to main memory block number. Okay, tag is equals to main memory block number. Okay, so now next point, size of tag is maximum in fully and minimum in diag mapping. Okay, so you see in yourself here that tag size is maximum, right? Tag size is maximum. There is no byte offset. There is no block offset. Okay, no block number, no set number. Okay, so tag is maximum here and minimum in the diagnostic, right? Minimum, where it is minimum in the diagnostic. Because why minimum in the diagnostic, why not in the set associative? Because you know na, see here, you know na that it is that here in the set associative comes into picture, right? So these bits will be anyway reduced further, right? Anyway reduced further, right? See here, sets will reduce, right? Set will increase, right? Set will increase, and then the set offset bits will be decreased, so that tag will be increased, right? Tag will be increased. Very good concept, very good concept. Now same thing for right, similar point of this, that index will be maximum in direct and minimum in fully. Like minimum is zero, like there is no index for it. Any block can go to anywhere, there is no index, but it is maximum in direct. Okay. Now, what is the advantage is it has the least conflict ratio, right? It has the least conflict ratio, and there is no conflict. Sorry, conflict misses. There is least conflict misses because you know now any block can go to anywhere, so least conflict misses. And it has best heat ratio. Okay. What is the disadvantage? Costly hardware and slow tech comparison. And costly hardware because you have to compare, like, comparators are more. Compare total number of comparators are more, right? Total number of comparators are more. So it is costly hardware. Got it? And slow tech comparison because this tech comparison requires time, right? It takes time. It takes time. It takes time. Okay. Now moving to the next point. There are three different type of misses, right? There are three different type of misses. Three different type of misses. Compulsory misses, conflict misses, and capacity miss, right? So compulsory miss is every time, like the first miss is compulsory. First miss is compulsory miss, right? Whenever the first miss happens is compulsory miss. Conflict miss I have told above, right? I have told above that if something is conflicting, then it is conflict miss. And if miss happens because of capacity, miss because of capacity because of capacity is called as capacity miss, right? Is called as capacity miss. Okay. Now here, to reduce the conflict miss, right? To reduce the conflict means you have to increase the associativity, right? Simple, right? You have to increase the associativity so that to increase the associativity so that many, right? So if let's say set contains two blocks, like, right, let's say four blocks. Now if you increase the associativity to six blocks, right? Six blocks, right? Which means that one set contains six blocks, so that many different blocks will be mapped here. So there is less conflict means, right? There is less conflict means. Now next point is to reduce the cold means. What is the cold means? Compulsory means, another name is cold means. You have to increase the block size. Okay, so if you increase the block size, Right. Yeah. What does it mean? Which means that, let's say, if initially your cache is empty, right? Initially the cache is empty, right? Cache is empty. Now if you request something, right? If you request something, so first miss is, right? There is nothing, right? There is nothing present here. So there will be a miss. There will be a miss, which means that nothing is present. If nothing is present, then there will be a miss, which means that that miss is called as cold miss. That miss is called as cold miss. But if you increase the block size, then many content, like too much of content, can be come, right? Can become like can become from main memory to cache, right? Because a block comes from main memory to cache, right? Your computer architecture. Like if there is a miss in the cache, you go to the main memory and then you fill the block, right? To fill the block. So if you increase this particular block size, right, many content, like too much data will be present, right? Many data, like more data will come, and more data will come, and less compulsory miss will be there, right? Less compulsory miss. Okay. To reduce the capacity means you have to increase the cache size, right? Nothing else. To reduce the capacity means you have to increase the size. You have to increase the total size. So this is one important point. Please take care. Please take care of this thing. Got it? Now moving to the next point. So these are the type of cache, right? There are four type of cache I have covered. Like there is a write through cache, write back, write allocate, and write non-allocate, right? So these are the type of caches. So let me tell you what it is. What is the write through cache, right? What is the write through cache? So what happens here? What happens when CPU adds the data, right? When CPU is adding the data, right? So this is the CPU, this is the cache memory, this is the main memory, right? So when CPU is writing the data, it updates the cache, right? It is update the cache and immediately updates main memory. So whenever CPU adds the data, right? Whenever CPU adds the data, it updates the cache and it updates the main memory. So both have same data, right? So both have same data at a time. Both have same data at a time. Okay. So this is the write through cache. This is the write through cache. Now write back cache. It is another name is write behind. Write behind. So what happens here when CPU adds the data, you update only in the cache, right? Update only in cache. Update only in cache. Here update in cache and immediately update in main memory both. Here, but in a write back you have to update only in cache, right? Update only in cache. Update main memory later when cache block is evicted. Okay. So here it is saving time. It is saving time. It is saving time. So here when a cache memory block is evicted, right? Because when a cache memory block is evicted, you have to update the main memory. Okay, because here this is the cache memory. Here if this is the cache memory, if this block is evicted, if this block is evicted, whatever the CPU have written, right? CPU have written this particular block, CPU have written, you have to update it to the main memory. You have updated to the main memory. Okay, to make it consistent, So when a cache block is evicted, you update the main memory, right? You update the main memory, Okay. Now it uses the dirty bit. Dirty is equals to modified but not returned to memory, right? So how it is able to know that when to replace, right? Like when to write in the main memory. So here I have told now that extra bits. These are the extra bits. This is the extra one type of extra bit. One type of extra bit. Dirty bit, right? So dirty bit here it is dirty bit. So from if this bit is one, if dirty bit equal to one, dirty equal to 0. right? If dirty bit equal to 1, you can able to get to know that this block is modified, right? This block is modified, and then you have to, this block is modified, this block is modified, right? Dirty equal to 1 means modified, okay? And then it is not written in the main memory, okay? With the help of dirty bit, you update the main memory. Now one another is write allocate. What is the write allocate? So what is the question? What if a write miss occurs, right? Like if you are writing it, if you are writing like CPU writes it, but if it is a miss, right? If it is a miss, write miss, right? Write miss. So if CPU is writing, but if it is a miss, then what to do? So what is the policy? Bring the block into the cache, then write into the cache. Okay. So bring block into the cache. First you have to bring the block. You have to bring the block into the cache, then you have to write it. So this is the flow. If write miss is there, then load the block into the cache and then write it. Okay. Load the block into the cache and then write it. First you load, then write. Okay. So it works best with the write back, right? It works best with the write back. This is the write back, right? So first you load into the cache, write it, but don't write in the main memory, right? Because what is the write back is don't write in the main memory, right? To save the time, to save the time. Okay, to save the time. Because here you see, write allocate can be worked with the write back or write to, right? But there is no point of using it with the write to, because write to it immediately updates the cache and main memory at a time, right? Both at a time. But it is wasting the time. So you are saving the time by using write allocate with the write back cache, right? Write back cache. Now what is okay? Now what is the write allocate? It another name is no write allocate. So what if a write miss occurs? Do not load block into the cache, write directly to main memory. So no load to cache directly updates the main memory, directly writes to main memory. So what is the flow? That if write means write to main memory only, write to main memory. Right. So you are not loading the block to the cache. Right. So it works best with the write through. It works best with the write through. Right. And you know, right, what is the write through? What is the write through? That you update the cache and main memory both at a time. Right. So for best performance, so this is line you have to remember. This is the concept, like, right, based if you know this, all the four, if you know their meaning, you can easily get to know that what it is mean. For the best performance, you have to use right through with no right allocate, right? Right through with no right allocate, and right back with right allocate, right back with right allocate. And I explained why you have to use right black with right allocate and right through with no right allocate. Okay, no right allocate. Because here in a right allocate, block comes to the block comes to the cache but not in the main memory. Right, and right back says that right here only in the cache, right? So here it's more like the saving the time by using it with the right back. Okay, and no right allocate says that do not load the block into the cache, just update in the main memory, right? Just update in the main memory. Okay, just update in the main memory. But to make it consistent with the cache, right? To make it consistent with the cache, we are using the write to, we are using the write to, we are using the write to, so that cache and main memory both contains the same data, same data, both contain same data, right? To make it consistent, to make it consistent. Got it. Now another good concept, another good concept. are coming, that what is the there is a two type of misses, local misses and one another is global miss also, right? So local miss and global miss. So what uh okay, so what is the meaning? What is the meaning? Let me tell meaning. Consider only one level, one case level, and ignores what happens elsewhere. Okay. And what is the global miss? It is related to all CPU main memory accesses, and it includes the effect of previous case level. Okay. So see, let's say you have levels of cache, right? So this is the level L1 cache, this is the L2 cache. Okay. Now here, let's say, okay, so let's say this one only. CPU makes 1000 memory references, 10,000 memory references, 10,000 memory references. Okay, and then here 1000, 1000 are missed, 1000 are missed, right? 1000 are missed, and 9000, right? 9000, okay, it is 90,000. 9,000 hit and 1,000 miss. Okay, 1,000 miss. Okay, and here for the L2 it is 50 misses and 950 hits. Right, 950 hits. Okay, so let's say this is the case that 10,000 memory references is given to the L1. So from the L1, 9,000 hit will be there and 1,000 miss will be there. If 1,000 miss will be there from the L1, 1,000 request goes to the L2, right? 1,000 request goes to the L2. Out of which 950 are hits and 50 are miss. So consider this. Consider. Okay. So what the local miss says? Local miss says that what is the local miss said? Miss is in this case divided by excesses to this case. Right? See this excesses to this case. It is local to it. It is local to it. So if I calculate local miss, if I calculate local miss for L1, so what is the miss in this case? 1000. Okay, 1000 miss in the L1. Excesses to this case. What are the excesses? 10,000 excesses. Yeah? 10,000 excesses. So this is the L1 miss, right? L1 local miss. What is the L2? How many miss in the L2? 50. How many excesses to L2 case? How many excesses to L2 case, right? So 1000, right? 1000. So this is the local miss for L1 and L2. So this is one concept. It is called as local miss, right? It is called as local miss. Now same, what is the global miss? What is the global miss? So global miss set is equal to misses in this case divided by total memory references by CPU. See, total memory references by CPU. Okay. So if I calculate global miss of L1, what is the misses in the case? How many misses in the L1 case? 1000 miss, right? 1000 miss. The 1000 miss divided by total memory references. Like globally it will see, right? Globally it will see. Globally it will see. And here it will see locally. It will see locally. It will see each thing locally, but here it will see each thing globally. So 1000 total memory references. How many total memory references? 10,000. Okay. For the L2, how many misses? 50 misses. Right. And how many total memory references? 10,000. Right. 10,000 memory references. So this is, in this way you can calculate global miss and local miss, right? And these are the concepts that like what is the global miss and local miss. They are the question like yeah, 1 to gate questions are there related to this concept. So I have covered it. Okay, so please take care. Please take care. Please take care. Global and local miss. Okay. Now moving to the next point. What is the Now moving to the next point, what is the average memory access time? Right? What is the average memory access time? So this is one another concept related to access time of cache, right? Access time of cache and main memory. So average time taken to AMAT, which means that average memory access time. Its full form is average, yeah, because someone might miss this. That's why I write it here. Average memory access time. So average time taken to access the memory, considering both hit and misses, because sometimes data is in the cache, so it will be a fast, and sometimes it is not, right? So it is not. So which means miss. So it is slow. Okay, so sometimes it is fast, sometimes it is slow. So what is the average time to access the memory? Right? What is the average time to access the memory? It is called as average memory access time. So this is the formulas for it. This is the formulas for it. No need to remember anything. Like I will tell you what is the basic average memory access time formula. So it is most important that if miss penalty is given in the question, what is the miss penalty? What is the miss penalty? So what is the miss penalty? Extra time to bring the block from lower memory, right? Extra time to bring the block from lower memory, which means that main memory. So time to bring, right? Time to bring the block from lower memory. So whatever the extra time, not only just to bring, right? Not only to bring, but extra time like you are checking the main memory, right? You are accessing it, you are taking, and then the entire extra time is called as miss penalty, right? So if miss penalty is given in the question, then what is the average memory access time? It is the hit time plus miss set into miss penalty, right? It is the hit time plus miss set into miss penalty. So hit time you have to anyway you have to include it. You have to include it anyway. Okay, you have to include it anyway. Then plus what? How many extra time? How many extra time? So miss it into miss penalty. I hope you know this thing. I hope you know this thing. I don't have to deep dive this particular formula. Okay. Now what is the average memory access time formula if two levels of cache is given? Like sorry for that. Okay. So average memory access time formula if two levels of cache is given. So let's say here L1 is given and here L2 is given and main memory. Okay. And here CPU. So if let's say this is the diagram, then first CPU will access. CPU will access. So CPU access is the L1. CPU access is the L1. So either it is a hit or it is a miss. Or it is a miss. Right? If it is a miss, then it goes to the L2. Then either it will be a hit and it will be a miss. If it is a miss, then it goes to the main memory. Right? This is the this is the diagram you have to make in any of the question. Like CPU access is L1, then hit, then L1 access time, right? L1 access time. Okay, L1 access time. Now if it is a miss, then it goes to the L2. It goes to the L2. So L2 hit, so L2 access time, L2 access time. But if it is a miss, right? Miss in L1. Okay, miss in L1 goes to the L2. So now it is miss in L2. It goes to the main memory. Right? So here main memory access time. Got it? So simple. So what is the average memory access time for it? So let's say this is the H1, right? This is the miss one of miss set of L1, right? and it is the heat rate of L2. It is the miss rate of L2. Okay, heat rate and miss rate I have written, nothing else. Okay, so now how to find it? So let's say this excess time of L1. So see here, L1 heat time, or you can say that excess time, right? Excess time and heat time both are same. So this is T1. Got it? What is the heat time of L2? L2 excess time. So here T2 is given, and here main memory. Okay. Okay. Now see, what is the average memory access time? H1 into T1, right? H1 into T1. Okay, H1 into T1, right? Because heat rate into heat time, right? Because if it is a heat, then heat rate into heat time, right? You know, heat rate into heat time. Okay, what if it is a miss? What is if it is a miss? So M1, right? M1 into how much this thing, right? M1 into now two paths are there. So let me go into this path. So if we go to this path, then heat rate H2 into T1 plus T2, right? T1 plus T2. So T2 for accessing, but here we have accessed one time. See here also we have accessed L1. So L1 access time, right? So T1 plus T2. Okay, because first we are accessing L1, then we are accessing L2. Got it? And then we got a hit. Now take the third one. Take the third path. Now if we take the third path, so this is the okay. Let me take yellow color. This is the third part. If we take, then if it right, so m1 we have multiplied. Now if it is a miss, right, if it is a miss, so m2 into t1 plus t2 plus tmn. So here it is t1 plus t2 plus main memory, right? So here you check, you first access into L1, you then access into, if miss happens, then you access into the L2, and at last you access the main memory, right? So total time, got it? And here T1 plus T2, and here it is T1. Okay, so if you know this, if you have made this now, if you have made this thing, you can easily write average memory access time formula, right? Average memory access time formula you can easily write. No need to remember. No need to remember. And only know this particular formula, right? There is no any other formula for average memory access time. Like you can find many different types of like simultaneous access and hierarchical type of terms are there, but I will tell you that no gate question ask or and it is not standard concept, and also not standard concept. Which one? Simultaneous or hierarchical? That there is no standard concept, there is no kind of this thing, this keyword in the gate PYQs as well, right? Gate PYQs. So no need to take any tension, no need to take any tension. Just remember this particular formula, right? Or just to understand it. No need to remember also, right? There is no need to remember. You just have to understand it intuitively. Understand it intuitively. Okay. One another point here. Here, if number of read is given and write instructions are given, and different hit and misses are also given for read and write, then this is the average memory access time. Like how many read instruction into its average time, and how many read instruction percentage of write instruction into its average time. Okay? So percentage of read into its access time, percentage of write into its access time. Got it? Now moving to the next question. I sorry, next particular point. So there are three type of policies: inclusion policy, exclusive policy, and non-exclusion policy. Right. So what is inclusion policy says? All data is L1 is guaranteed to be present in L2. L2 is a superset of L1, but effective cache capacity is reduced because of duplicated block. Right. Okay. So here, if multiple levels of caches is given, so this is L1, this is L2, this is main memory, and as you know that, right, if you go this way, right, size will increase, right? So all data is present. What inclusion policy says? All the data is present in L1 is going to be present in L2, right? So L2 is a superset of L1. Okay, but effective cache capacity, right? So what it means, effective cache capacity, right? So effectively, so it will reduce because duplicate things, right? Because of the duplicated block L1 and L2 both, L1 and L2 both, right? Blocks present in L1 and L2 both. That's why. Not very easy concept. Okay. So see here, L1 is the subset of L2. L1 is the subset of L2. Okay. Now next one. What is the exclusive? L1 intersection L2 is equals to empty. So no block is duplicated here. No block is duplicated between L1 and L2. A block either exists in L1 or L2 but never both. Okay. So either a block exists in either in L1 or L2 but not both. So intersection is empty. So it gives the maximum effective cache capacity, right? Maximum effective cache capacity it gives. Exclusive, right? Exclusive cache. And the third one is non-exclusive. So L1 is not a subset of L2, right? L1 is not a subset of L2. So there is no strict requirement that L1 block must exist in L2. It provides the better effective cache size and less duplication of data. Okay, so either here non-exclusive means either L1 block present or not present or not present. Like there is no any fixed thing, right? There is not either it will be some blocks may be present, some blocks may not be present. Like it is the combination. It is the combination of both. You can imagine that it is a combination of both inclusion, inclusion and exclusion, right? And do you know that which particular policy is used in our day-to-day life? Right? You are amazed by hearing that this non-inclusive is used, non-inclusive used, right? Currently, like inclusive case is also not used, exclusive also not, but this is non-inclusive case used currently, used now. Okay, so this is the concept which you have to take care. Got it? Hello. So moving to the moving to the next topic, which is pipelining. Right. So what is the pipelining? So execution of multiple instructions overlapped in time, just like an assembly line. Right? Like one instruction is in execute, next is in decode, next is in fetch. So uh, what is the pipelining? If I say in normal term, let's say you have one particular thing, right? Let's say you have okay. So let's say you have one unit which do washing and dyeing and folding, right? This is one machine, right? This is one machine. If this is one machine, then each clothes, right? If this is one machine, then each clothes have to go first to washing, then to drying and folding. Okay, then folding, and then if it goes completely to it, then only the next thing can perform it. Like after the washing, drying, and folding can be completed, then only you can perform the next thing. But if you pipeline it, like let's say if you have divided this task. Let's say this is the washing machine, and then this is the dyeing machine, right? You have separated these three particular tasks to three different machines, and this is the folding machine, right? So whichever clothes have been washed, they goes to the dye, right? But now washing is free, right? Now washing machine is free, so you can put more clothes into washing machine, while other clothes are in dyeing, other clothes are in the folding, right? So this is called as pipelining. This is called as pipelining, right? So here you are doing the things parallelly, but here you have to wait for it, right? See here, only one machine does washing, drying, and folding. So even though washing task has completed, you can't use the washing task, right? Because this machine only able to perform the next particular operation only when this three task has been completed. But if you separated out each task, then if the washing ta- if this washing machine is free, you can utilize that because this is free. You can utilize while other clothes are present in dyeing and folding. So this is the pipelining. Okay. Now it is there is one classic five-state pipeline. There is a classic five-state pipeline like instruction, fetch, decode, execute, memory, and write. Okay. So I hope you know this thing. I don't have to tell much thing here. Like it is instruction fetch, then instruction decode and register. It will happen in the next stage. It's called as ID stage. Then execute stage in which execution will happen ALU, right? And fourth stage is memory access. Like memory access stage. Like if you want to access the memory, then that is the stage. Okay, and the last one is the write back stage. The last one is the write back stage. Like if you are writing back to the register, okay, so writing back to the register. So that is the last stage. Back to the register or main memory. Writing back to the register or main memory. So these are the classical five-step pipeline. This information will be given in the question, but it is better if you know it. It is better if you know it. Got it. Now, why pipelining? Right? First question is why pipelining? So it improves the throughput, right? Instruction per unit time. It increases the throughput. What is the throughput means? How many instruction executed per unit time, right? Per unit time. How many instructions executed, right? How many instruction executed per unit time? How many instruction executed per unit time? That is called as throughput. So here, if you see this pipelining, if you have pipelined it, right? So per unit of time, many instruction can be executed, right? Because one instruction can execute here, instruction can execute here. So it improves the throughput. It does not reduce the single instruction latency, right? It does not reduce the single instruction latency. But see why? Because if you have only single instruction, right? Only single instruction, then it will also take washing time and drying time plus folding time in pipeline. Okay, it will take both the time washing plus drying plus folding. If you see non-pipeline, this is non-pipeline. Here also same time washing plus drying plus folding. So you are not improving. You are not improving anything if you have single instruction. Okay. Now this is the pipeline time for n instruction that k plus n minus 1 cycles and then like if you have n instruction, right? If you have n instruction. So okay, okay. I was looking for a space. Yeah. So let's say you have n instructions. So if you have k stages, right? If you have k stages, kth stage, right? So one instruction will take each stage. Like first instruction will take this, right? So k cycles. Now, as soon as first instruction reaches here, second instruction reaches here, third here, fourth here, fifth here, sixth here, right? Because pipelining because all these stages are free, right? All these stages are free. So as soon as first instruction reaches the last stage, the second instruction will reach on the previous stage, the third its previous, fourth its previous. Okay. So for the rest, n minus one instruction. So these are the, let's say, n minus one instruction. It will take one cycle each. So this much time you are saving, right? This much time you are saving. So for the first instruction, it takes k cycle plus for the rest n minus one instruction, it will take one cycle to execute. So this many cycles into, you want to know what is the pipeline time. So into cycle time. TP is cycle time. Right? TP is cycle time. See here. TP is pipeline clock period or cycle time. Time taken for one pipeline stage. Right? Time taken for one pipeline stage in pipeline execution. Right? So it is called as cycle time or pipeline time. You can say pipeline time or cycle time. Got it? That is called as TP. So if you are multiplied with the TP, you can able to get that what is the total pipeline time. Okay, very easy, right? Very easy. If you, yeah, see here in everything, right? In the gate examination, in each particular thing in the computer architecture also, don't mug up things. Like if you remember it intuitively, if you know the concept intuitively, you can solve any question. Got it? Now what is the speed up? Speed up is how much improvement, right? How much improvement. So speed up is equals to non-pipeline time, non-pipeline time divided by pipeline time, right? Non-pipeline time divided by pipeline time. So this is the formula for non-pipeline, and for this is formula for pipeline, and n into tn it is for non-pipeline, and because t n into tn, so each instruction takes n. So if you have n instruction, right? If you have n instruction, so each instruction takes tn time, right? So see from this washing machine example, each instruction takes this much time. Each takes this one. So n instruction will take this much time. Got it? Because there is one single machine, so each instruction will go for each of these tasks. So n into tn. But if you look up the idle speed up, so let's say n into tn plus k plus n minus 1 into tp. So let's say your n is infinite, n tends to infinite. So this and this thing you can remove. And what is the idle speed up equal to tn divided by tp. So in this way you can calculate it. Okay. Okay. So please take this thing also. What is the speed up and what is the idle speed up? Now TP I have told that TP equal to pipeline clock period or cycle time. Right? Now what is the TN? Time taken to execute one instruction without pipeline. Right? One instruction without pipeline, which is also called as non-pipeline. Now there is a formula for it. What is the TP? It is maximum segment delay plus register delay. So let's say these are the segments. These are the segment, and in between there is a register. Right? There is a register. These are the segment. So what is the TP? TP is equal to maximum of all the segment delay plus only one register delay, right? One register delay. One register delay. Okay. What is the TN? What is the TN? Sum of all segment delay, right? Because it have to go to each of the segment. It have to go to each of the segment, right? So sum of all the segment delay. So that is called as like in this way you can calculate TP and TN. Okay. Now what is the throughput? Throughput is number of instruction executed per second. I told you above. So number of per unit time, how many instruction executed, right? So most probably per unit time means per second. Or it is based on the question. Like in a question, if it is given something else, then you have to take per unit time accordingly. Right. So throughput is number of instruction executed per second. Right. So yeah, one more thing. Uh, You may tell that why here register delay is not included, right? So here registers are not required, right? Registers are not required. Here register delays are not required. Right. So this thing, please take care. TP and TN, TP and TN. Please take care how to calculate it, right? How to calculate it. Now, what is the latency of pipeline? What is the latency of pipeline? TP. What is the latency of non-pipeline? TN. Right? Latency means time. Latency means time. What is the throughput? It is 1 divided by TP. Okay. So, uh, see, if you don't have to remember what is the throughput, then you can think like that. That K plus N minus 1 into TP. This much time you can able to execute N instruction. Right? N instruction. So what is the throughput per unit of time? So per unit 1 second. Let's say 1 second. How much time? Okay, 1 second. How much time? So it will be n divided by k plus n minus 1 into TP. Okay. So this is the throughput. But every time, please remember this. Please remember this point. You have to first make this kind of thing, and then you have to eliminate this n. You have to eliminate this n if n is not given. Right? If n is not given, if n value is not given, n value not given, then you eliminate. N value not given, then you can eliminate it. So you cancel this thing because you can assume that n is infinite, right? N is infinite. So it turns out to be 1 divided by TP. 1 divided by TP. See, throughput. Okay. So no need to remember. No need to remember anything. You can derive also, right? You can derive the things also. No need to remember. Now, pipeline hazard. This is one another good concept, and questions are also coming. So condition that prevents next instruction from executing in the next cycle. So there might be some different kind of conditions, okay, that prevents the next instruction from executing in the next cycle. So there are three type of hazards: structural hazard, data hazard, and control hazard. Okay, so what is structural hazard? So when two or more pipeline states need the same hardware at the same time, right? So if there is a two or more pipeline stages are there, right? There are more two or more pipeline stages are there, and if they need the same hardware, if they need the same hardware at the same time, right? Which means that here resource constraints are there, then it is called a structural hazard, right? Hazard meaning some condition which will which prevents from executing it. So see here only at all condition that prevents the instruction from executing. Okay, so hazard is that kind of condition. It is called as one, like any of the condition which can prevent it from executing is called as hazard. Okay, now next one is data hazard. So occurs when instruction depends on the result of the previous instruction. Okay, so here let's say this is instruction I1, I2, I3. So I4, like right. So if I4 instruction is dependent on I2, I4 instruction is dependent on I2. So this one is called as data hazard, right? So there might be data hazard. It's called as data dependency. I will tell you about in some point of time. Right now, what is the control hazard? Control hazard means it occurs due to branch instruction, right? If there is a branch instruction, then control hazards can occur, right? Can occur. Now see this thing, that there are three type of dependencies. First one is row, which is also called as read after write. This is also called as true dependency. Another is write after read, which is also called as anti dependency. And the last one is write after add, which is also called as output dependency. And both WAR and WAW are also called as false dependency, right? So please remember these terms. Okay, so let me tell you what is row dependency, what is WAR dependency, what is WAW dependency. Okay, so all this data dependency occurs between instruction, right? Data dependencies occurs between instruction. And please take care this between instruction. Keep remember this point between instruction and only between instruction. So what is read after write? So which means that you are reading the value after writing it. So let's say I1 equal to R2 plus R3 is given, and here R4 is there, right? So here you are reading the value of I1 after writing, right? After writing. So this is the dependency. So let's say this is instruction I1, this is instruction I2. Okay. So this is called as dependency, right? This is called as dependency. So this is called as zero dependency. Okay. One more point I have to tell you that let's say if this is the case, I1 if given something like this thing, I4, right? So here one row dependency. So if someone asks you that how many row dependencies will be here, right? Someone asks you how many row dependencies here, what you will answer? I1 to I1 and here also I1 to I1. So two row dependencies. Answer is wrong, right? Answer is wrong. No. Only one row dependency, only one. Because I have told you here, see, data dependency, these are the data dependencies. It occurs between instruction, right? Between instructions. So between I1 and I2 instruction, there can be only one, at most one, right? At most one. Okay, so one row dependency, not two. Got it? Please take care this thing. Now what is the WA right after it, right? What is the right after it dependency? So you are writing it after reading it. Okay, so let's say you have something like this thing. Now I am changing here. So you are writing it after reading, right? After reading, you are writing it. So R2 have dependency. See, R2 have dependency. So for R2, you are reading it after writing, right? Sorry, you are writing it after reading. So you are here reading it, then you are writing it. So one WAR dependencies. Okay. So you have to check this way. Got it? Now what is WW? It is right after right, which means that if I1 is R2, R3, and another instruction is R2, I1. So you are writing it after writing it, right? You are writing it after writing. So right after right, right after right. So this way you can find the dependency. So if someone asks you how to calculate row dependency, you have to look in this way. If someone asks what is the var dependency, you have to look this way, right? You have to look this way. Like if any dependencies, if WAWS, you have to look in this way. Like so for in exam, how to do it fast. That's why I was saying these things. Okay. I hope you know this thing all. Got it? So there are these three dependencies, and these two dependencies won't create hazard, won't create hazard, and won't create data hazard. Keep this thing in mind. Keep this thing in mind. Only row dependencies create because only row creates. Okay, because these two can be eliminated. These two dependencies can be eliminated. So yeah. Okay, so see here. Only row dependencies create row hazard. WAW and WR won't create any hazard, right? Won't create any hazard. So here if someone asks that how many dependencies, how many dependencies, right? For example, so 1 plus 1 plus 1, which will be 3. If someone asks how many hazard, so only one, right? Only one. Only one plus 0, so 1. Okay, so how to calculate hazard, right? See, these dependencies may or may create hazard. So the answer 1 is also wrong, right? Answer 1 is also wrong. If you have answered it blindly, it is wrong. But 0 and 0, it is 2. 0 and 0 plus 0, it is 2. Here, no 0. Here, it is also 0 and here also 0. Hazard. Okay. But you have to check manually. If row dependencies are there, right? If let's say you have found out that there are 4 dependencies, right? 4 row dependencies, then you have to make the pipeline and then you have to check that if any problem is there or not. If any problem, then it creates the row hazard. I have covered this type of questions in EPT rank improvement course. Right? Please watch it. Please watch it. I have covered in very depth, like how you have to how you get to know that whether the hazard is there or not. Right? How you get to know whether it creates hazard or not. So you have to make the pipeline, and then you have to see the things. If any problem occurs, then if any problem occurs, then it is low hazard. Okay. So both WAW and WR dependencies can be eliminated by register renaming. So if you rename it, those these both dependencies can be eliminated. So for row dependencies, these are the techniques which can be used: bypassing, stall, which is also called as bubble, and instruction reordering, which compiler does. Right? These can be used. Okay, what is open forwarding? Now, what is open forwarding? It is hardware solution for data dependencies by compiler. Right? It is provided by compiler. So as soon as open forwarding, so as soon as you calculated it, so you just forward this thing immediately, right, to the next stage. That is called as open forwarding. As soon as as soon as you calculate it, you immediately forward it, right? You immediately forward it. It is called as open forwarding. Okay. Now, this is one point you have to remember now. CPI is equal to 1 plus stall frequency into stall cycle. Okay, so if let's say there are the questions in which uh, something related to frequencies and some stalls will be given. So this is the case in which you have to calculate CPI, which is cycle per instruction. Cycle per instruction. Per instruction, how many cycles it takes. So one is one plus extra, right? One plus extra. Okay. Now one instruction execution time, which is CPI average into its cycle time, right? Cycle into cycle time, right? Cycle into cycle time. CPI, you know it. CPI is per instruction how many cycle it takes into TP means cycle time. Okay. Now this thing stall because of the branch instruction equal to I minus one. If after I stage the condition is evaluated. So if let's say if after the fifth stage condition is evaluated, so how many stall? 5 minus 1, which is 4 stalls. Okay. I have also covered this type of questions in the IIC. Please take care. Please see it. Please see it if you haven't. If you haven't. Okay. Even the branch is not taken, then two stalls are there due to branch instruction, right? Yeah, so even the branch is not taken, but then also stalls are there due to branch instruction, right? Because to get to know that whether it is branch or not, stalls are required. Okay, stalls are required. Okay, so now next point: result of the branch condition evaluated happen after the execution phase of branch instruction. Okay, so when the branch condition evaluation happens after the execution stage, EX stage, after EX stage. Okay. After EX stage, you can get to know that what is the effective address, like where to jump, where to jump. Also, if it is a branch condition, then you can able to know that where it will jump and what is the outcome of the condition and what is the outcome after the EX stage. Okay. So these are the points you need to take when revising the pipeline, right? These got it? Okay. So now moving to the next one. Moving to the next topic. So disk. It is a very simple topic. You just have to go through this particular formula. There is no much things, right? So let's just tell. Okay. So see every you know now you know this disk, right? You know this disk. What? Okay. Let's say this is the something like this. Please forgive me for this diagram. This is keep on rotating, and this is the arm assembly, and this is the head. Right? This is the head. So something like of this disc diagram. Right? This is the disc diagram. This is the plate. This is the plate. Okay. Here there are, this is the plate. On each one, this is the tag. Okay, this is the tag. This is the sector. Got it? This is the sector. Okay, this is the head. This is the head. Okay. Okay, so tag is the circular path. Sector is the smallest chunk in a smallest chunk. Right? This is the smallest chunk in a particular tag. Cylinder is the same radius tag. Right? So if I combine this particular thing, same radius tag. Right? If I combine this thing, combine this thing. If I combine this thing, right? So this thing is called as one cylinder, same radius. This one is called as another cylinder. This another is called as another cylinder, right? So same radius stack is called as cylinder, right? Same radius stack is called as cylinder. Okay. Each surface has one reader head, and at a time only one is active. See here, each surface have one reader head. See here, one, right? And only one can activate at a time. How many? Okay, now next point. Total number of surface is equals to 2 into number of platters. So let's say 3 platters, so one front and one back. So 2. 2 into number of platter. Okay. Now what is the sector of tag? Sector of tag and disk sector, right? Sector of tag and disk sector both are same. Got it? Now sector is the smallest addressable unit of disk which can be read or written at a once. So at a once, sector is the smallest addressable unit, right? Which can be read or written at once. Okay. Now see this thing. Now this is the disk capacity formula. 2 into number of letters, it will give you total number of surfaces. Right? In a one surface, how many tags are there? Okay. Multiplied by tags per surface. Multiplied by how many sectors are there per tag, right? Per tag. Let's say this is a one tag. So this is one tag. How many sectors are there? How many sectors are there? Into sector capacity, right? What is the sector capacity? What is the sector capacity for this thing? If you multiplied all this term, you can able to get disk capacity, right? You will able to get disk capacity. So this is the very easy formula. Just have to multiply it intuitively. So you can remember it intuitively. There is no much, nothing to mug up. Okay, now disk access time. So disk access time is equal to, hello, yeah, disk access time is equal to seek time plus rotational latency plus one sector transfer time, right? Plus one sector transfer time plus other delay. So disk access time, which means that seek time plus rotational latency plus what is the one sector transfer time and other delay. So take zero if nothing mentioned in the question, right? You have to take the zero if nothing mentioned in the question. I have covered this this question, this type of every question I have covered in the IIC. Please watch it if you haven't. So what is the seek time? And what is the seek time? Seek time means that a time takes by head to move to the particular cylinder, right? To move to the particular cylinder is called as seek time, which means that let's say if this is the case, right, and read it. So whether to go here on this particular tag, whether to go on this particular tag, whether to go on this particular tag. So that is called as seek time. That is called as seek time, like where to go, like right, where to go. Now, what is the rotational latency? Rotational latency means takes time it takes by time it takes so that this particular sector comes to the read-write head, right? Because it keeps on rotating. So once you finalize this particular tag, right? Once you finalize this particular tag, okay. Now this sector to comes under read-write head, right? This sector to comes under this read-write head, to comes under this read-write head. That time is called as rotational latency. Okay. So you are waiting for it, like when it is rotation, when rotation is going on, you are waiting that when a particular sector comes under reader head. Okay. And then you transfer that particular sector. So one sector transfer that. Got it? So this is the formula. Average rotational latency equal to rotation time divided by 2. And one sector transfer time is equal to rotation time divided by sectors per turn. Okay. And this is the formula you have to take care. You can easily find rotation time based on the revolution. Like, let's say if it is given that 6,000 revolution per minute, right? Something like of this information is given. So 6,000 revolution, 60 second, 6,000 revolution, right? So 1 second. Okay, so per revolution, per rotation, how much time? So 60 divided by 6,000. Okay. So this is the time you can inject here. So that's called as one evolution time or one rotation time. Okay, and this will be given in the question. RPM or some type of some information is given. So if you take the average, you can able to get average rotational latency. Okay. Now we use the concept of cylinder to store the file so that seek time required only once, right? So that seek time required only once. We use the concept of cylinder to store the file. Okay, I have told that. So seek time only consider one. So see, once your reader head will be under this particular cylinder. So your reader have to go to this tag, then you can able to get this information. Then on this cylinder, on this particular tag on this cylinder, okay? Because cylinder contains of same radius, right? Same radius tag. Got it? So we use the concept of cylinders. We use the concept of cylinder to store the file so that seek time required only once. Okay. Now, how many cylinders? So number of tags per surface, right? How many total number of tags are there? Those many number of cylinders. Okay. Now next point. Sequentially stored n sector transfer time, right? So if you stored sequentially, right? So seek time plus rotational latency plus n into one sector transfer time, right? Because n sectors are there, right? Because you stored it sequentially. Okay. Now if you stored it randomly, n into seek time plus rotational latency plus one sector transfer time, right? Because you don't know. See here, n sectors, right? You have stored the file on the n sectors randomly, right? You don't know, like whether your file is present. Let's say if this is the disk, right? Let's say this is the disk. Got it? If this is the disk, you don't know that you are present here. You have something is present here, something is present here, something here randomly. Okay. So for each of the n sector, you first have to go to particular seek, right? You have to go to particular tag, then it will take the rotational latency for it, and then you transfer the time, right? Then you transfer it. So randomly, if you stored it, then for each of the n, you take seek time plus rotational latency plus sector transfer time. Okay. Now, please take care this. Please take care this point. Got it? Now disk addressing. Like disk addressing will be having this format like CHS, which means cycle cylinder number, then surface number, then sector number. Like what is the cylinder number, and then what is the surface number, and then what is the sector number. Okay. So if you want to find sector number for a given address, so C into how many sectors per cylinder you have traversed. Okay, so CHS, which means that how many sectors you have crossed across, right? You have crossed across plus H into. Okay, so now you are in the current cylinder. Okay, So, so this conditioning we are dealing with the sectors, right? This conditioning we are dealing with the number of sectors. Okay. So if you have CHS, which means that C into sectors per cylinder, right? Sectors per cylinder you have traversed plus H into H into plus S. Okay, plus H into, which means that now you are at the steel cylinder, right? You have here now you are at steel cylinder. Now which surface, right? How many surfaces? So H surface you have come across, and how many sectors? So each surface meaning one track. Got it? Because this is the cylinder. Right? If let's say this is the cylinder, okay, this is the sixth cylinder. This is the sixth cylinder. Now let's say this is the eighth surface, right? Eighth surface. So this one surface you have covered across. Okay. So H into sectors per track plus on this surface on eighth surface which particular sector, right? So this is the sector number like S1, S2, S3, S4. Okay, which sector? Okay. So this is the formula. This is the formula for it. Got it? So by this way you can able to find out that C equal to sector number divided by sectors per cylinder. Like let's say with the help of this you can able to find what is the sector number. Okay. Now this is the reverse from sector number to CHS. It is this formula is used for CHS to sector number. Okay, so if you have sector number, you divided by sectors per cylinder, you will get the C. Okay. Now whatever sector numbers are left, you mod it with the sectors per cylinder, so you got the left sectors, left sectors. You divided by sectors per track, you get the surface number H. Okay. Now you mod it again. You mod it again. Whatever the left sectors, that is your S. That is your S. Okay. This thing can be able to get only when if you do the question, right? Only when you do the question. So please do the question. Please do the gate PYQs. Gate PYQs do. Gate PYQs. Do it. Okay. Now next point. Cylinder equal to set of tracks at the same radius on all the surface, right? So I told you same radius tracks. Okay. Same radius tracks. What is the seek time? That is also I told. Movement between the cylinders, not tracks, right? So movement between the cylinders. Now disk scheduling is used to have minimum seek time, right? Disk scheduling is used. So there is disk something called as disk scheduling is used here to minimize the seek time. So let's say you have many requests. You have many requests R1, R2, R3, R4, and Rn. So in what way to fulfill such that seek is minimum, right? Seek is minimum. So disk scheduling algo comes. Disk scheduling algo comes into picture, right? Comes. So these are the different disk scheduling algorithm. FCFS, first come first serve, shortest seek time for scan, C scan, look, and C look. FCFS, you know that first request to be fulfilled in manner. Okay. What is the SSTF? SSTF is shortest seek time first. Shortest seek time first, right? Shortest seek time first. What does it mean? Uh, what does it mean by shortest seek time? So if you are currently if you are currently fulfill this request now, whether to go this side or this side, so whichever takes the minimum seek, you fulfill that, right? Minimum seek fulfill first. Okay. Minimum seek fulfill first. So that is called as SST. Minimum seek fulfill first. Not that. Now Now scan, C scan, look and C look. So this diagram I have taken from my IIC course. IIC course. Okay. So in what the scan does? Scan goes in this way. So let's say your radiate head will be here. It goes at the one end. So this is the chosen end. See, this direction is the chosen end first initially. Okay. So it goes till the end. It goes till the end. It fulfills each and every one. Then it goes to the next other direction and it fulfills the request and it comes back. Comes back means to fulfill the request. Okay. Now what the C scan does, here also the direction is this way. So it starts with this way, but it won't fulfill in this direction. It will fulfill here, it will fulfill here, it will fulfill here, it will fulfill here. It won't fulfill in this direction. In this direction it won't fulfill. Okay, then in this direction again it will fulfill. Okay, in this direction again it will fulfill. Got it. So here in both you have to choose the direction. See here you have chosen the direction. So in this direction only it will fulfill it. It will fulfill. It will fulfill. So see this scan, this both the scan it goes till the end. Right? It goes till the end. Okay. Now coming back to the look. Okay. Now what is the look? So see look is similar version of scan, but let me take white. But look eliminates this particular thing, right? Because let's say if you don't have to fulfill these particular parts, then it won't go till the end, right? Look goes till the required is present in one direction, right? See here, looks goes till the request is present in one direction, right? Till the request is present. So in one direction, if the request is present, until only it will go. It won't go till the end, right? It won't go. Not all the time. Not all time it goes till the end. And not all the time it goes till the end. Till the request it goes. So here see, it goes, then it comes back, and then here it will fulfill. So here it had fulfilled here, here, and here. Now CLOOK is similar version of CSCAN. It fulfills only in one direction. So it fulfills here, it fulfills here, and because the direction chosen is this one. Okay. So it has fulfilled here and it has fulfilled here, and it also haven't gone till the end. Okay. So it is the version of look. Okay. So I hope you got it. What is scan? C scan, look and see. See, look, okay. It's a good concept, and many gate PYQs are also coming with this topic. So please know these things. Okay. Okay, moving to the next topic, floating point operations. Moving to the next topic, floating point operations. So floating point representation is used to represent floating point numbers. Right? Used to represent float numbers. So a number is represented in the form of S, E, and Mantissa. S, E, and Mantissa. Okay. S is for sign, either positive or negative, right? Either it is positive or negative, 1 or 0. Exponent is biased, right? So this exponent is biased exponent. Mantissa is normalized, and this bit represents how many digits after point. So after decimal, okay, so after point, how many digits? How many digits? So this represents Mantissa. This is represented by Mantissa. Okay. So if the more bits in exponent, which means that it has larger range, right? If more bits is present in exponent, it means larger range. Okay, okay. Now next point, more bits in Mantissa. If the more bits in Mantissa, which means that greater precision or accuracy, right? Because see here, if more bits are present after the point, which means that it has It has good precision and accuracy. Okay, greater precision and accuracy. Now next point, what is the actual exponent? So stored exponent minus bias. See here I have told that exponent is bias. So what the how you can find the actual exponent? Stored exponent e. This is called as e minus. You have to subtract from the bias, right? Then you can able to get that what is the actual exponent. Okay, okay. So now next point. This is the one good point. This is the one good point that bias if not given can be calculated as 2 power k minus 1 minus 1. Okay, where k equal to exponent bits. So if it is given that 6 bits, then bias is equal to 2 power 6 minus 1 minus 1, which will be 63. Okay, 2 power 5 minus 1, 31. Bias is equal to 31. Okay, in this way you have to calculate it. Yep. Okay. Now next point, by default, explicit normalization, if nothing is given in the question, right? If nothing is given in the question, by default explicit normalization you have to use. What is the formula for it? These two are the formulas for explicit normalization and implicit normalization. Okay. See, minus one. This is power s into here explicit. You have to add 0 point. For the implicit, you have to add 1 point as e minus. This is the actual exponent. Right? Got it. So these two are the formulas for explicit normalization and implicit normalization. Okay. Now next point. Okay. So now next point is IEEE 754. There are the two type of question is given. Either question with the IEEE 754, like they will give the standard, or without it. Okay. So if without it, then they either must say that whether to use explicit normalization or implicit normalization. If nothing is mentioned, then explicit. Okay. Okay. So here you have to remember this thing and this point that for IEEE 754, single precision it contains 32 bits, bias is 127, sign is 1 bit, exponent 8 bits, mantissa is 26. So see how bias is calculated: 2 power 8 minus 1 minus 1, 2 power 7 minus 1, which will be 127. Okay, bias. Okay, so for IEEE 754, double precision it is of 64 bits, bias is 1023, and sign 1 bit, exponent 11, and mantissa 52 bits. So you have to remember this thing. Maybe they will not give this particular information because these are the proper standard, right? These are the standard. So you have to remember it. And IEEE 754, it uses the implicit normalization, right? Implicit normalization. It uses the implicit normalization, which means that 1 point m, 1 point m. Okay. So whenever it this is value, you have to use 1 point m. Okay. Now next point, that special number. So there is a special number. There is a special number. So all zeros and all ones you don't have to use. See here I will tell. So all zeros and all ones is used for zero, infinity, and all. So you don't have to use those are the special numbers. Okay, they are the special numbers. Like exponent, all zeros and all ones you don't have to use that. E, C, E bits, capital E bits, capital E. Okay, okay. Now next point. Conventional representation cannot store zero and very small numbers. Okay, so if you have conventional representation, it cannot store zero and very small number. So I was checking if everything is working. Yeah, so it cannot store zero and very small number. So see here, see in this particular point, here it is largest negative number, it is smallest positive number. Here largest positive number and here smallest negative number. So before this thing, these are the overflow, and in between this thing, this is the underflow. Okay. So conventional representation, this representation cannot store very small numbers, which is overflow and underflow. Right? They won't store very small and very big number. Okay, overflow number. Yeah, very small and very big, and very big. Got it. Now next point. See, this is called minus zero to something related to plus zero. This is called as denormalized number. And from 0 plus 0 to infinite is called as normalized number, and from here on this side minus 0 to minus infinity is also called as normalized number. Okay, so please keep these things in mind. Okay, please keep these things in mind. Okay, so for denormalized number, these are the formulas here. 1 point m, 1 point m, when t is exponent is fixed here, when the exponent is fixed here, minus 126 for single precision and minus 1022 for double precision. So this is fixed, right? This is fixed. So please remember, you don't have to here. You don't have to understand it anything. You have to remember it things, all the things. Okay. So now this is one chart. It's from my IIC course. Okay. So this is the chart. See. So let's say this is the one case. This is the exponent field. This is the Mantissa field. And what it represents, and here is the formula. So if it is a normalized number, so I told that what is the normalized number? These are the normalized number. So here normalized number, exponent is not all zeros and all ones. Mantissa can be any value. It represents normal number, right? And formula is this one. Okay, for a normalized, right? Formula is this one. Okay. Yeah, I think here also formula E minus 127. Okay, so here I told about IEEE 754, right? IEEE 754. IEEE 754. Okay, so here formula is this, and here you don't have to use all, here don't use not all zeros and all ones. See, because all zeros and all ones are used for spatial number. I have told you, right? All zeros and all ones are used for spatial number. What is the denormalized? Denormalized is exponent all zeros, Mantissa can be non-zero, and it represents a very small number near to zero. See here, that I have told, no? What is the denormalized number? Very small number near to zero, right? Near to zero. And this is the value for it. Right? This is the value for it. Like single precision. Okay. Now how to represent zero? I think it here it will be 1 point. Here it will be 1 point. Maybe I have used here general term like 0 point m. Here explicit normalization I used. I think. Okay, so how to represent zero, infinity, and not a number? So zero means all zeros, zero, and plus or minus zero, right? Based on the sign. For infinite, it will be all ones, exponent all ones, Mantissa is all zero. It represents infinity, plus and minus infinity. For not a number, exponent is all ones, Mantissa is not all zeros. It represents not a number, which means zero by zero case or some other, right? And there is no formula for it. There is no formula for it. Okay, so please remember it. Remember it. Remember it. Right? There is no other option. No other option. There is no other option. Just please remember this formula because these are the special cases. Right? These are the special cases. So please remember it. Okay, okay. Now, next topic will be the memory organization. Okay, one thing I have to tell here. Okay, so one thing I have to tell here. Uh, I'm looking into this formula. I'm looking into this formula of denormalized whether I meet the whether right. So here this formula is correct. This formula is correct. Like 0 point m into e into e minus 126, and you know, right, that exponent is all zero, so here you can inject e equal to 0 also. Okay, so it turns out to be 2 into minus 126. Okay, there is no issue for that here, but here I think it will be 0 point m, right? It will be 0 point m. Okay, it will be 0 point m. Got it? Yeah, so that's thing. Okay, so next one is memory organization. Next one is memory organization. uh, okay, so let's just start memory organization. So this is the memory hierarchy design. This is the memory hierarchy design. So let's say, see here, it's the level 1 CPU register, then RAM, SM, then DRAM, then disk, optical disk, and magnetic tape. So if you go down by this level, then increase in capacity, right? So you will be find out that capacity will increase and time also will increase. Okay. If you go by this way, which means that cost will increase, right? Cost increases. If you go in this way, right, if you go above, then cost will increases. If you go down, then capacity increases, right? Capacity increases. So yeah, you have to only remember this thing only. Okay, so by default, so yeah, so let's start with this two types. There is the two type of memory, like main memory, byte and word addressable, which I told you in the first in prerequisite, right? Byte addressable and word addressable. So by default, memory is byte addressable, which means that one address contains one byte, right? I told these things, right? In word addressable, one address contains one word. Okay. In word addressable, one 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 address contains one word. Okay. Now, what is the byte addressable memory? If you have 256 KB, which means that 256K locations, and each location contains one byte per location data, right? Per location data, one byte. So you can represent that you have 256K locations and each location contains one byte with 8 bits, right? One byte, one byte, one byte. Okay. So in this way, memory or byte addressable memory can be represented. Okay. Now this thing also I have covered. Word size equal to number of bits CPU processes at once, right? What is the address bit? Log 2 into number of addresses. Okay. So log into 256k. So 2 power 8 into 2 power 10, 18. So 18 bits. 18 bits. Decoder. Decoder is used to access the specific cell using addresses. This you know. And decoder is used to access the specific cell using the addresses. Decoder is used here. Here decoder is used. 18 cross 2 power 18 decoder is used here. Decoder to get to select a particular address, right? To select a particular address. Now there are two type of RAM, SRAM and DRAM. SRAM doesn't require refresh operation as it is made of flip-flops, while DRAM requires the refresh operation as it is made of capacitors, which stores the data in form of charges, right? And it requires the periodic refreshing because it forms the and because it stores the data in form of charges, right? Because it stores the data in form of charges, and charge will disappear on time to time, right? Charges will disappear on time to time. It requires periodic refreshing, right? It requires periodic refreshing. So DRAM requires the refreshing. Okay. So let's say let one refresh period have X amount of read write and Y amount of refresh. Okay. So let's say this is one refresh period read write and refresh. Okay, refresh. It is called as one refresh period. One refresh period. Okay, so here read write happens, then refresh happens, then again read write happens. Something like it is going on, right? It is going on. Read write, refresh, read write, refresh, read write, refresh, something like that. So this is one refresh. This is one refresh period. Okay, this is one refresh period. So what is the percentage of time for refresh? So let's say here it is called that X amount of time is read write and Y amount is for refresh. So what is the time for refresh? Y divided by what is the X plus Y into 100%? It's simple. It is simple. Okay. This is the important. This is the important point. This is the important point. In one refresh operation, one entire rows of cell are refreshed. Right? So if this is the cell and it has these rows, this has these rows, this entire cell, right? And this one is rows. So one entire rows of cell are refreshed, right? So one chip refresh time is equal to number of rows into refresh operation time, right? One entire rows of cell. So what is the chip refresh time? How many total number of rows? Total rows into refresh time. Chip refresh time equal to total rows into refresh time, right? Total rows into refresh time. Okay. Also, all chips are refreshed parallelly, right? All chips are refreshed parallelly. So let's say you have five chips. Chip one, 2, 3, 4, 5. Okay. So all the five chips C1, C2, C3, 4, and 5 are refreshed parallelly. So one chip refresh time is equals to n chip refresh time. Okay. So all the chips refresh parallelly. All the chips refresh parallelly. So this is the time for five chip refresh also. So because all the chips refresh parallelly. Got it? Nothing else. It's a very good concept. Please remember it. Okay, so next point. In multiple chip memory, one decode output selects one entire horizontal line. Right? So if let's say if multiple chip is there, let's say this multiple chip is there, right? Multiple chip is there, and let's say your decoder here is the decoder. Decoder has selected this line, so this entire line will be extracted. Right? This entire cell line will be extracted. Okay, from this chip also, from this C1 chip also, and C2 chip also. So this is Here saying one decode outputs select one entire horizontal alignment. So this is horizontal alignment and it selects one entire horizontal alignment. Okay. Now next point, if required addresses are more, and if you want more addresses, then vertical arrangements are used like this way, so that these addresses will be more. Right? Vertical arrangements are used. Okay, but if you require more data, then horizontal arrangement is used. Then horizontal arrangement is used if you require more data. Okay, if required address and data both used, then hybrid arrangement is used. Right? Then hybrid arrangement is used. Now, what is the default storage unit? It is bits. Right? Default storage unit is bits. Now, this thing is the main point. This thing is the main point. If data is of multiple bytes, there are two ways to store. Right? If data is the multiple bytes, there are two ways to store. First is little and big India. So what is the little India? It starts with the little end or LSB. Okay. What is the big India? Starts with the big end or MSB, which means that let's say you have something like mm, 1, 2, 3, 4. Okay. Your x is equals to 1, 2, 3, 4, which means 0, 0. Okay. So this x is of multiple byte data, right? Multiple byte data. Okay, let's say here hexadecimal, right? 0x. Let's say I1. I1 contains 0x, 0x1, 2, 3, 4. Okay. It is a multiple byte data. So in a memory, how it stores. So for little end, it starts with the little end, which means LSB. So let's say you have 100, then 104, then 108, then 112. This memory location. Okay. So how it stores in the little, it starts with the LSB. So this is the LSB. Okay. So it will store like this with zero. It will be here, and 0011 will be here. 0010 will be here. 0001. Okay. But if it is a big end, it starts with the MSB. It starts with the MSB. So 0001, 0010, 1101, 0. So this is the representation, right? This is the Indian name representation. This is the representation. Okay, this is the representation. So Indianness comes into play picture only when you have multiple bytes. Yeah, please take care. This only when you have multiple bytes. When you have multiple bytes, then only Indianness comes into picture. Okay. I have I have took down many good questions in the rank improvement course related to this topic. So please watch it if you haven't till now. Okay. So it only applies to primitive data items. It only applies to primitive data items, not to array, stack, or strings. Right. This thing also please take care. It only applies to primitive data item, not to array, stack, or string. So what does it mean? Not to array, stack, or string, which means that let's say array is given 1, 2, 3, 4. Okay, so array is given 1, 2, 3, 4. Right? So you can't store this thing 104, 108, 102. So if it is a little and start with the little, so 4, 3, 2, 1, and then big end is 1, 2, 3, 4. Right? It is a little and it is a big. So you can't store in this way. This is entirely wrong. This is entirely wrong. Okay, this is entirely wrong. But if you zoom this thing, if you zoom it, right, now it will be 0, 0, 0, 0. It will be 0, 0, 0, 0. It will be 0, 0, 0, 0, 0, 0, 1. So this order is fixed, right? This order is fixed. This order is fixed But if you zoom this each particular data, now this is the multi-byte, this is the multi-byte. See here now, if data is of multiple bytes, then two ways to store. And here also it comes into picture only when you have multiple bytes. Right? Now you have multiple bytes. Now you can store it. Now you can store it. Now you can store it. So because here I was assuming that one integer is of 4 byte, right? One integer is of 4 byte. So that's why it is a multiple byte data. And then here this thing I can store either in little or in big. Okay. So that's why this array struct and string, it not applies endianness, but if you zoom it, then it internally applies because here order is fixed. Order is fixed. Okay. So just take care these things, right? Now moving to the next topic. Okay, so these are the addressing modes and instructions. Instruction topic. So instructions and addressing mode. So a binary pattern that tells the CPU what operation to perform and on which data, right? It is called an instruction. This is called an instruction. Which is a binary pattern. Yeah, everything is working. Yep. A binary pattern that tells. Okay, I'm sure your screen is showing. Yeah. I just offered one. A binary pattern that tells the CPU what operation to perform and on which data. Okay. A pattern which tells the CPU what operation to perform is called as instruction. So this is the instruction. This is the instruction. So here opcode is there, then operand is there, then addressing mode, right? Then it is the addressing mode. So this is the one instruction, right? This is the instruction in bits. So what is the opcode? Opcode is the operation code, right? Opcode is operation code. Operation code. So opcode means operation. What are the different operation? Add, subtraction, load, and different. Okay. So if opcode is of n bits, then number of unique operations CPU can perform equal to maximum number of instruction and n. Okay. So let's say if opcode is n bits, right? So here if opcode is n bits, then how many different operations can perform? 2 power n, right? 2 power n operations. 2 power n operation means 2 power n instructions, right? Because each different operations consist of one instruction. Okay. Now, what is the ISA? ISA is instruction and architecture. Is a set of all type of instructions supported by the CPU, right? So all type of instruction which is supported by CPU. So if your system, like your computer architecture also contains ISA and CPU don't understand anything other than ISA. Okay, please take care of this thing. CPU only understand only those instructions which is written in the ISA, which is written in the ISA. Got it? What is the operand? Operand is data or address. Either it is a data or it is address. And what is the addressing mode? How to locate it, right? How to locate the operand? How to locate the operand? So if you have variable length instruction, if you have variable length instruction, then fixed length opcode. If you have fixed length instruction, then variable length opcode. Okay. Okay. So here there are different type of instructions. So first one is data transfer. So move, load, store, push, and pop. Another is there is no thing to say. Arithmetic, add, subtract, multiply, division, increment, decrement. Logical is AND or XOR, NOT, and shift. Control and branch, jump, branch if equal, branch if not equal, call, and return. And so these are the different instructions. It's just a type of instruction. There can be many more. Okay. So now addressing modes. What are the different addressing modes? Okay. So addressing mode is equal to how effective address how the if addressing mode is how the effective address or operand address or target address of operand is calculated, right? So effective address meaning target address or operand address is calculated, right? What is the effective what is the effective address? It is also called as operand address, also it is called as target address. Okay. So addressing mode is equal to formula for effective address, formula for operand address, which means how the address of the operand can be calculated. Okay, what is the formula for it? That is called as addressing mode. So first one is immediate addressing. Immediate addressing, which means move I1 phi, right? So phi is the value. Okay. So direct immediate. Okay, immediate. So I1 contains phi. Direct addressing, which means that effective address equal to address in the instruction. So move I1 comma 1000 location. So you go to the 1000 location, you get the value and you store it in the I1. Okay. That is direct addressing. What is indirect? Effective address equal to memory at address you have to move. So move I1 comma this thing, which means that you go to 1000, right? You will get one different location. You go to that another location, and then on this location I1 you will store it. I1 you store it. Okay, like two times you have to go to the memory. Here one time, here two times. Access register addressing. So operand in the register, right? So I1, yeah, I2 contains the operand and it comes to the I1. Register indirect addressing. So content of R2 is the effective address. So R2 contains the effective address. So if you go to the that memory location, you will get the operand, right? You will get the operand, and it is just an example of different instructions. Okay. What is the index instruction? Index addressing. Index meaning index register, right? So base address plus index register. So here, if you what how the effective address will calculated a plus what R2, right? A plus whatever the value contains in the R2. So it is called as index register, called as index addressing. Okay, so mainly it is used to access the used in as used to access uh, index register. See here. Okay. Now another is base addressing or displacement addressing. So here base register is the base meaning base register, index meaning index register plus offset, right? Plus offset. If you add it, then you will get to know effective address. Okay. Now PC relative. PC relative means PC register, right? PC register plus offset. Okay. Now one another mode is auto increment and auto decrement mode. It's like plus plus and minus minus. Automatically it will do increment and automatically it will do decrement. Okay. Now the next one is implied or implicit addressing. So what does it mean? Operand is implied or accumulator. Means operand is implied. So for example, accumulator. So if you this thing clear A, which means that automatically you will get to know that operand is present in accumulator. You have to clear it. You have to clear it, right? So what is used in the branch? What is used in the branch? PC relative, right? PC relative is also called as relative addressing, and it is used in the branch. And what is used in the IS? What is used in the IS? Index or base addressing mode. Okay. So yeah, these are the different addressing modes. I hope you know all of it, and I hope you got it. The different addressing modes. Okay. CPU, control unit, and DM and interrupts. Yeah, good to go. So many topics are there in the computer architecture. Yeah. See here now another topic is risk versus CISC, right? So risk means reduced instruction set architecture and CISC means complex instruction set architecture. So here this is my diagram for IIC code. I have explained it well, and I also uh, make this one so you can both contains the point different points. Okay, so you just have to remember it, or you can understand also, right? Remember or understand it intuitively. Okay, I explained very well in my this course. So what the risk and what the risk means. Risk risk means reduced instruction set computer, and the risk means complex instruction set computer. So what is our focus in risk? Our focus of risk is in single simple instruction. Okay. So if I talk about previous times, right? So before earlier times, what happens is that memory is earlier memory is costlier, not time. So CISC is used, right? So complex instructions are used. Complex instruction is used. Complex instruction is used so that memory is used less, right? So that memory is used less. Okay, but nowadays, time is costlier, not memory. Okay, so risk is used. Risk is used. Reduced instruction set computer, right? Because here there are simple instruction. Because memory is not costlier nowadays. Memory is cheaper, right? Memory is cheaper, so that uh, you can have many instruction. You can have many instruction in the memory, and here there are no complex instruction. Right? There are no complex instruction, so that time will be less. Okay, so let's just see the point. In the is simple instruction, fixed length instruction, simple and limited addressing mode, less instruction, easy to implement, right? Using hardwired control unit, which I will tell you further. Then one cycle per instruction, register to register, and more number of register are used. Okay? So here everything is simple, right? Everything is simple, so that time is utilized efficiently. Here, but in says complex instruction, variable length, complex addressing mode, more number of instructions, difficult to implement, multiple cycles are there, then less number of registers, register to memory and memory to register arithmetic operations are there. So here focus is on to reduce memory. Okay, so let's just see what I have explained. Okay, see register to register executed in one clock cycle, very fast, right? Very fast. Then minimize the execution time. It is not hardware heavy, it is easy, right? Assembly programmer life is hard because here they have to add the simple code. Eh? You have to add, they don't have to add complex things, so that they have to see many things. Here pipelining is easy. Here more registers. Okay. If I look into sys, then it is memory instruction. Then it needs to access the memory. And it needs to access the memory and hence takes many clock cycles. It minimizes the size of the program. Right? It see here it focus is to minimize the size of the program. Okay. Here focus is to minimize the execution time. Okay. Here it is hardware heavy. Here, application programmer life is easy because complex instructions are supported. So, assembly programmer can write it faster. Here, less registers are used, and here pipelining is hard. So, these are the points of risk versus risk. Right? Okay, so next topic is CPU and control unit. So one cycle time is equals to 1 divided by clock rate, right? 1 divided by clock rate. This is the standard formula. Then one instruction execution time equal to CPI into cycle time. This I have told above also, that if one instruction takes like how many cycles, okay, CPI equal to cycles per instruction, right? Cycles per instruction. So per instruction total cycles into cycle time. Okay. Then program execution time is equals to what is the program n instruction into CPI into cycle time. Okay. Now MIPS. What is the MIPS? MIPS equal to million instruction per second. Okay, million instruction per second. Yeah, you just have to remember this thing, but you can easily calculate it when it comes to the question. Okay. There is no hard thing here. Now two CPU having same instruction set can have different CPI and clock rate. Okay. If let's say two CPU has been given and have same ISA like instruction set, they may have different CPI and the clock rate. Okay. So keep remember this. Okay. So now what is the control unit? What is the control unit? It diets the fetch, decode, execute cycle. Okay, control unit, right? So it generates the control signal. See, it generates the control signal for ALU, register, memory, IO. Okay, different. It generates the control signal. I told you in the first that there is a control bus, right? Control bus, and there is a control bus. So I have told in the first prerequisite that there is a control bus. It is able to send the control signals, right? Its job is to transfer the control signal, and this control unit job is to generate the control signal, right? It generate and here it transfers or sends control signal. Okay, so it decides the sequence of micro operation, right? It decides the sequence of micro operation, which means that first this thing to perform, then this thing to perform, then this thing, then this thing, then this thing. So it decides the sequence, right? It decides the sequence. So there are two type of control unit. First one is that hardwired and microprogram, right? Hardwired and microprogram. So hardwired and microprogram. So hardwired means that control signals generated using the logic gate, right? Using the logic gate, control signals are generated, and it is faster in execution and difficult to modify, right? Because everything is hardwired, right? It is using with the hardwired, and it is difficult to modify, and it is faster execution because it is generated using the help of logic gates, and you know that logic gates are faster, right? Logic gates are faster. Okay. Now what is the microprogram control unit? So they stored micro control signals stored as micro instructions executed by control memory and easy to modify, slower than hardwired, right? It is easy to modify, slower than hardwired, right? So what is the microprogram, the control unit? So here everything is, yeah, control signal is stored in terms of micro instructions. See here micro instructions are there. Micro instructions are there. And control signal stored in it. Control signals stored in it. Okay. So see here micro instruction. What is micro instruction? Word in control memory, right? So there is something called as control memory. This is control memory. This is control memory, and it stores the micro instruction, right? It stores the micro instruction. Control memory job. Control memory. There is something called as control memory, and its job is to store the micro instruction. Okay, and it contains the control signal for one clock cycle. See, I told you it stores the control signal. Okay, micro instruction stores the control signal, and that is called as micro program control unit. Right? Micro program control unit. Right. What is the micro program now? So it is the sequence of micro instructions. It is one instruction. What is the micro program? It is the sequence of those micro instructions. Okay, sequence of micro instructions, and it implements one machine instruction. So one machine instruction contains sequence of micro instructions, which is also called as micro program. Right? This thing. Got it? So now there are two type of microprogramming. There are two type of microprogramming. First one is horizontal microprogramming and vertical. Horizontal microprogramming and vertical microprogramming. So in a horizontal microprogramming, there is a wide control word. There is one bit for each control signal. There is no decoding needed. It is faster and it is larger. It is large control memory. Okay. While if you see vertical microprogramming, it is encoded. It requires decoding. Its signals are grouped. It is compact. It is slower because here decoding is required, so it is slower, and here it is compact, right? Because the signals are grouped, right? Signals are grouped. But if you are see horizontal microprogramming, so here one bit for each control signal, right? One bit for each control signal. So it is faster also and larger control memory, and it is wider, right? Here it is wider, but here it is compact, right? Wider. See, this thing here it is wide, right? This is wider. So horizontal microprogramming and vertical microprogramming. So now if I talk about speed wise. So this is the hardwired has higher speed than microprogram, right? Microprogram. This is the microprogram type, right? In which also horizontal is faster because no decoding is needed. No decoding is needed, right? And then vertical because here decoding is needed, right? Decoding is needed. Okay. Okay. So now next one is control memory. So what is the control memory? It stores the microprogram and it is usually ROM, right? So ROM equal to control memory, right? Control memory. ROM and control memory both are same. Right? ROM and control memory both are same. It usually is the ROM. Okay. Now what is the CPU register? So there are the different type of CPU registers are there. PC means program counter, instruction register, memory address register, memory data register. Then this is called as flags, which contains zero, carry, overflow, sign, etc. Different flags, right? Different flags. So here it stores address, right? Memory it stores the data MDR. Instruction register, it stores the instruction which is fetched. That instruction fetched. Whichever the instruction you fetch, it is stored in the IR, right? And PC holds the address of the next instruction, right? All this, holds the address of, it holds the address of next instruction, right? It holds the address of next instruction. It holds the address of the next instruction. So these are the CPU registers and all the different type of control unit and different micro two type of units and all. Okay. Yeah. So everything is theoretical. So you have to understood it and so that you can easily grasp. Got it? Now this one is the last topic. I think yeah, there is no much things. This one is the last topic for today's session, like today's short note session. Right. So let's just start. So DMA and interrupts. Right? DMA and interrupt. So first one is program diode. Program diode. It is also called as polling. Right? It is also called as polling. So what does it mean? So CPU continuously checks the device status, right? So CPU continuously checks the device status. So what is the time taken here in the polling? Because it continuously polls, right? Continuously polls it. So time taken is time to check the status plus time to transfer the data, right? Because it continuously checks the status. So CPU remains busy here because you are wasting the cycle, right? You are wasting the cycle for for continuously polling. Here it is simple hardware, but it is least efficient, right? Yeah, here it is simple hardware, but least efficient because you are wasting the CPU cycle, right? You are wasting the CPU cycle. Got it? Okay. Now next one, interrupt driven IO. Interrupt driven IO. So what is there in the interrupt driven IO? So these are the IO, right? These are the IO types, IO methods. Okay. So it device interrupts the CPU when ready, right? So there is the CPU, there is the IO device. So IO interrupts the CPU. IO interrupts the CPU only when data is ready, right? Only when data ready. Only when data is ready. Okay. So what is the time taken here? Time taken is interrupt overhead plus time to service the interrupt, right? Time to service the interrupt. So what the interrupt overhead includes? See, it includes the context saving, then interrupt service routine execution, then context restoring. Okay. So I told you this thing that whenever interrupt occurs, then three step will be performed, right? So first one is that context will be saved. Then it goes to the interrupt service routine, right? So it is called as interrupt service routine. It will be executed and interrupt service routine will be executed and then context will be restored, right? Context will be restored. So three step for interrupts. Okay. So time to service the interrupt, yeah, and then these overhead, and then you have to service the interrupt also, right? You have to service the interrupt also. So time required for it. Okay. Now next point is better than polling, but still CPU involved is in every transfer, right? Yeah, it's better than polling because you don't have to continuously check that whether IO is ready, whether IO is ready. It interrupts when data is ready. Okay. So but still CPU is involved, right? But still CPU is involved in every transfer. Okay. So yeah, this is the interrupt driven IO. This is the interrupt driven IO. Now next one is DMA. Next one is DMA. So it used for high speed data transfer, right? High speed bulk data transfer. CPU sends to DMA controller. There is something called as DMA controller, right? DMA controller, and all the things done by DMA controller. So CPU send two information: starting address and what is the data count. Data count is number of words or bytes. Okay, which means that from this starting address, how many data it have to send, right? How many data it have to transfer. So what DMA controller will do? DMA controller, it generates the address, it sends the control signal to memory, and CPU is free doing the transfer, right? CPU is free doing the transfer because everything has been done by DMA. Everything done by DMA. Everything is done by DMA. Right, everything is done by DMA. So CPU is free doing that transfer, right? CPU is free doing the transfer. Okay. So CPU is free doing that transfer. Okay, so now uh, there are three different type of DMA transfer modes. Right? There are three different type of DMA transfer mode. The first one is that burst mode. So DMA controller takes the control of the bus for the entire block transfer. Right? DMA controller takes the control of the block for the entire block transfer. So when it has to transfer entire block, DMA controller takes the entire control of the bus. Okay. Okay, so due to which CPU waits until the DMA finish, right? CPU have to wait because it takes the entire control DMA controller takes. Okay, so now what is the percentage of time CPU is blocked? Percentage of time CPU is blocked. So transfer time divided by preparation time plus transfer time, right? So it's like transfer time divided by total time. Okay, so fast transfer here, but CPU blocked longer, right? But CPU have to be blocked long, right? But CPU have to block. for longer time, right? But CPU blockage is there. Here CPU blockage is there. Okay. Next one. Next one is cycle stealing mode. Okay, cycle stealing mode. So DMA controller steals one bus cycle at a time, right? DMA controller steals one bus cycle at a time. CPU execution slows down but does not stop, right? So what here? It steals one bus cycle at a time, right? See here what happens when it have to transfer, it takes entire control in a burst, right? So that's why it is burst one. Its name only suggests burst. Here cycle stealing, its name suggests that it steals the cycle, it steals the cycle, it steals the cycle. Okay. So CPU execution slows down but does not stop, right? So CPU execution slows down but does not stop because one cycle it steals, then one cycle CPU, then something like that. Okay. One or maybe two cycle it steals, one cycle it steals, something like that. Okay. So here also see percentage of block will be transfer time divided by preparation time only. Okay. Only preparation time, not total time. Okay. Please keep this thing in mind. And here CPU waits less than burst mode. Yeah, CPU have to wait less because it steals only a cycle, only cycles, not at a time, not at a time. Okay, not at a time transfers entire thing. Got that? Okay, okay. So the third one is interleaving mode. The third one is interleaving mode. So here CPU and DMA controller use different memory modules. Okay, it use different memory modules. No CPU waiting or blocking is used. No CPU waiting or blocking. It is best performance among all the DMA modes. Right? Best performance among all the DMA modes. So here interleaving mode in which that they both use. So CPU use different memory modules, DMA controller use different memory modules. Okay, so in that way both are interleaved, right? So no CPU waiting or blocking is there. Got it? Right. Now last one is DMA key points, right? So what are the DMA key points? So DMA is the fastest method for IO memory data transfer, right? IO to memory data transfer. DMA is the fastest method. At a time, only one of CPU or DMA controller can use system buses, right? At a time, only one of either CPU or DMA controller can use system buses. Okay. Then next point, DMA transfer can occur during instruction execution. Right? DMA transfer can occur during instruction execution. So DMA transfer can occur during instruction execution. DMA transfer can occur. Okay, it cannot occur. Okay, so one important it can occur during instruction execution. DMA transfer can occur, but it cannot occur. It cannot occur during interrupt service routing, right? During ISR. Interrupt service routing, it cannot occur. DMA transfer. Okay. And this thing, one important point is that what is the maximum data transferred without CPU intervention? So if X is the number of bits in the data count register, that is the data count. If X is the number of bits, what is the maximum data it can transfer? 2 power X minus 1, right? 2 power X minus 1 data it can transfer. Okay, 2 power X minus 1 data it can transfer. Okay. Now, this is the last point. What is the CPU efficiency? What is the CPU efficiency order from least to most? So program IO was the least efficient, then interrupt IO because here you have to wait too much. Okay, so program IO, and this is the program IO polling. Okay, then interrupt IO, then DMA, right? Then DMA. It is fastest. It is fastest. But if the in the interrupt IO, it interrupts CPU only when data is ready. Okay, only when data is ready. Okay, only when data is ready. Yeah, so this is the CPU efficiency order. Yeah, please take care of these things. Okay, yeah, so with this note, short notes is over. Short notes over. I hope I have covered each and every different points and I have able to explain you each and everything, right? I think many things we have covered. Where does it go on? Yeah, many things we have covered, right? And many important points and all the short notes, entire short notes has been covered now, right? Entire short notes. If you have, if you see this one time, then your entire COA will be revised, right? So this thing is done, right? So yeah, so yeah, we'll end the lecture, but before that, I want to say that please keep on work hard, right? Because now the days are very less, and this one is the exam which can change your life, which can change your entire life, right? So please give everything to it. Please have the motivation high. This time, you will be in a very less low mode, right? Like many other things, like is affecting marks is not coming and all those. But at this time, you have to be high motivation, right? High motivation. See, look at your family, look at your mother, father, like why you started. If this time the motivation is very high, then you will be able to tackle each and everything, right? Able to tackle each and everything, right? Able to tackle each and every and difficulties, difficulties. So please keep your motive high and wish you all the best for the upcoming gate examination. And till then, keep on learning the things. Yeah, I'm ending the session now.